Welcome to another deep dive. Today we'll be unraveling a new method proposed for electromagnetic scattering problems.
Sounds exciting.
It is. We'll be looking at excerpts from a novel, highly parallelizable machine learning-based method for the fast solution of integral equations for electromagnetic scattering problems.
Ah, yes. By Ines Kos, Mert Kalfa, Cicely Dogan, and Vakur B. Ertürk.
Right. Just published on January 9th, 2025. From what I've read, they're bringing machine learning to the table to address some pretty fundamental computational challenges. What are your initial thoughts?
Well, as you know, solving integral equations for these scattering problems, especially with complex and large-scale objects, can be computationally very demanding.
Yeah, it gets intense quickly. And it's not just theoretical, right? These scattering problems have real-world implications.
Absolutely. Take antenna design, for example. Understanding how electromagnetic waves scatter is crucial for optimizing antenna performance.
So making them more efficient and giving them better radiation patterns.
Exactly. And then there's radar technology. Scattering analysis is at the heart of how radar systems detect and track targets.
Right. And how about medical imaging? MRI, for instance.
Even there, understanding scattering helps reconstruct images from the received signal. So it's a pretty fundamental problem across a wide range of technologies.
It really is. Now, the paper mentions the method of moments, or MOM. Can you give us a quick rundown of that?
Sure. MOM is a classic technique for solving those integral equations we talked about. But as the objects get more complex and larger, MOM calculations can become a real bottleneck.
Computationally expensive, you mean?
Exactly. It gets slow, which is where faster methods like the multi-level fast multipole algorithm, MLFMA, come in.
MLFMA, that's the go-to for speeding things up, right?
Right.
But I understand it has its own limitations.
It does, especially at low frequencies. It's prone to something called the low frequency breakdown, the LFB problem.
Ah, so even our shortcut has its weaknesses. That's where this new method enters the scene.
Yes, the authors present a three-stage method. It's a really clever blend of mathematical manipulation and machine learning, and they've designed it to be highly parallelizable.
Parallelizable meaning, sorry, I just want to make sure everyone's on the same page here.
No problem.
Yeah.
It essentially means you can break the problem into smaller chunks and solve them simultaneously on multiple processors.
Like a team working on different parts of a project at the same time.
A perfect analogy. And the authors claim their method has strong scalability. The more processors you add, the faster it gets, almost proportionally.
That's really powerful. But how do they actually achieve this? What's the secret sauce?
It all starts with how they structure the problem. Their first stage involves mapping the scattering problem to what they call uniform basis functions.
Uniform basis functions. What exactly does that entail?
Imagine you take any scattering object, no matter how complex its shape, and divide it into a bunch of identical boxes.
Kind of like simplifying the geometry into these building blocks.
Exactly. Then they represent what's happening electromagnetically within each box using these tiny idealized antennas called Hertzian dipoles.
I remember those from my electromagnetism courses. So every box gets the same dipole treatment, regardless of what the original object looked like.
Precisely. That uniformity is key. It creates identical computational units, making it easy to distribute the calculations across multiple processors.
I'm starting to see how the parallelization works. It's like an assembly line,
Right.
with each processor working on its own box.
A very efficient assembly line. Now, this mapping to uniform basis functions is just the first step. The second stage is where machine learning comes in. They call it translation.
Translation. So they're using machine learning to, translate between these simplified boxes and the actual scattering interactions.
You got it. Traditionally, calculating those interactions involves something called the dyadic Green's function. It basically describes how electromagnetic waves travel from one point to another.
Okay, but why not just calculate that function directly? Why bring machine learning into the picture?
Well, calculating the dyadic Green's function for every single interaction between boxes can be computationally very expensive, especially when you have a large number of boxes.
So they're using machine learning to take a shortcut.
In a way, yes. They train these complex valued fully connected neural networks, or CVFCNNs, to approximate the dyadic Green's function. The networks learn the complex relationships between inputs and outputs so they can make accurate predictions without doing all those tedious calculations.
So they're teaching the networks to predict how those Hertzian dipoles in different boxes interact with each other.
Precisely. And that saves a ton of computation time, especially for large-scale problems.
Very clever. And how do they train these networks to be so accurate?
They use a two-stage process. First, they train on a dataset of uniformly generated interactions covering a wide range of possibilities. This gives the network a good general understanding.
Like foundational training for an athlete.
A great analogy. Then, they fine-tune the network using a dataset of pseudo-randomly generated surface interactions. This tailors it to handle the specific types of interactions it's likely to encounter in real-world problems.
So it gets both broad knowledge and specialized skills. Makes sense. Now we've mapped the problem, translated the interactions using machine learning. What's the final step?
The last stage is mapping the calculated fields back to the original subdomain basis functions. Essentially, translating the results from the simplified box world back to the complexity of the real object.
So they're putting the pieces back together after analyzing them in a more manageable form.
Exactly. It ensures the accuracy and relevance of the final solution, and this entire process, from mapping to translation to inverse mapping, is designed with parallelization in mind. The identical box structure allows for very efficient distribution of computations across multiple processors.
Impressive. So they've essentially streamlined the whole process. Now, they make some bold claims about the benefits of this method. What are some of the key advantages they highlight?
Well, first and foremost, the strong scalability for parallelization, as we've been discussing. It leads to significantly faster computations, especially for those large and complex objects that would take forever with traditional methods.
It's all about speed and efficiency.
That's a big part of it. But they also claim it effectively tackles the low-frequency breakdown problem, which, as we discussed, is a major limitation of traditional MLFMA.
Ah, right. That was a big sticking point. How do they manage to avoid that?
By directly incorporating the Hertzian dipole-Green's function in their training, they sidestep the numerical instabilities that plague MLFMA at low frequencies.
It's like they've found a clever workaround.
Precisely. And there's another big advantage. They emphasize the versatility of their method. Once you've trained these CVF-CNNs, you can apply them to a wide range of scattering objects and integral equation formulations.
So you don't have to retrain the networks for every new problem.
Exactly. That saves a huge amount of time and effort. It's like having a multi-tool that works on a variety of tasks.
Sounds promising. But we all know theoretical claims are one thing, real-world performance is another. Did they actually put this method to the test?
They did. The paper presents a series of numerical experiments designed to validate its accuracy, efficiency, and robustness. They tested it on various objects, comparing their results to established methods like MLFMA, and even analytical solutions were available.
Okay, so they didn't just talk the talk, they walked the walk. Let's dive into those numerical experiments and see how this method actually performed in practice.
Let's do it. We'll start with their benchmark test, using a simple Peck sphere.
A perfectly conducting sphere, the classic test case, right? Why choose that one?
Because it has a well-known analytical solution, the Me series. It gives them a reliable ground truth to compare their results against.
So they're setting a high bar for themselves right from the start. How did they fare in this benchmark test?
Exceptionally well. Their results matched both the Me series solution and the conventional MLFMA almost perfectly.
That's a good start. But a sphere is a pretty ideal case. Did they test it on anything more complex?
They did. They moved on to dielectric spheres, which are more representative of real-world objects. These have different material properties compared to a perfect conductor.
And how did it handle that added complexity?
Again, very well. They tested single-layer and two-layer dielectric spheres and found excellent agreement with analytical solutions.
So it can handle variations in material properties? That's promising.
Yeah.
But did they push it further? Did they try it on even more complex shapes?
Oh, absolutely. They chose two objects known to be particularly challenging for traditional methods.
Yeah.
The NASA almond and the Flam model.
I've heard of those. They're those high aspect ratio objects, right?
That's right. They're much longer in one dimension than the others, which makes them tricky for methods like MLFMA, which rely on hierarchical decomposition.
So it's like trying to fit a square peg in a round hole.
In a way, yes. But their method, with its uniform box structure, seems to handle these cases much more naturally.
That's intriguing. Did they compare its performance to MLFMA for these challenging shapes?
They did, and the results were pretty remarkable. For both the NASA almond and the Flam model, their methods significantly outperformed MLFMA in terms of computation time, even when using a single processor core.
So even without leveraging the full power of parallelization, it's already faster for these complex shapes.
Exactly. It highlights the inherent efficiency of their method structure.
Okay, so we've established that it's fast and accurate. especially for complex geometries. But what about that low-frequency breakdown issue? Did they actually demonstrate that their method overcomes that?
They did. They went back to that PEX skier, but this time they tested it at an extremely low frequency, 7.8125 millihertz.
To really put it to the test.
Exactly. And they trained their neural network specifically for this low-frequency scenario. The results were clear. Their method's prediction matched the ME-series solution perfectly, with no signs of the breakdown that would typically occur with MLFMA.
So they've got speed, accuracy, and a solution for the low-frequency breakdown problem. It all sounds pretty impressive. Are there any downsides? What are some of the limitations they acknowledge?
One limitation they point out is that their current implementation isn't hierarchical. The uniform box structure works great up to a certain size, but it might become less efficient for truly massive problems.
So it's like trying to build a skyscraper with Lego bricks. It works for a small model, but for a full-scale building, you need a more sophisticated approach.
A perfect analogy. And they do mention that they're already working on incorporating a hierarchical structure into their method.
Makes sense. Trying to scale up without adding some hierarchy would probably get messy.
Absolutely. But they also acknowledge that adding hierarchy might impact the strong scalability they've achieved.
Ah, right. Hierarchy usually means introducing dependencies between computations, which can limit parallelization.
Exactly. It's a trade-off they're exploring. But even if the strong scalability is slightly affected, they believe their approach will still be far more efficient than traditional methods.
Sounds like there's a lot of exciting research still to be done in this area.
Absolutely. This paper lays a strong foundation for a new generation of methods for solving electromagnetic scattering problems. It's a great example of what's possible when you combine rigorous mathematical modeling with cutting-edge machine learning.
It's been fascinating to delve into the technical details of this new method, but I'm curious about the bigger picture. What does this all mean for the future of those fields that rely so heavily on solving these scattering problems?
That's a great question. In the next part of our deep dive, let's explore the potential impact of this research on areas like antenna design, radar technology, and medical imaging.
All right, we left off talking about how this new method tackles those tricky high aspect ratio objects like the NASA almond and the FLAM model. It seems like their uniform box approach is giving them a real edge over traditional MLFMA in those cases. What were some of the specific results that jumped out at you?
I think what's really impressive is not just the speed improvement, but the consistency of the results. Take a look at figures 12 and 13. They've got visualizations of the far-field electric fields and the surface current density. For both the FLAM and the NASA almond, the results from their method almost perfectly overlay the results from the 4-level MLFMA.
Oh, I see it, yeah. So it's not just that the numbers are close, but the actual field patterns that they're predicting are almost identical. That's a really good indicator of accuracy.
Exactly. It really suggests that the method is capturing the physics accurately, not just finding some numerical shortcut to an answer that happens to be similar.
And speaking of those numerical shortcuts, the paper mentions that their method really shines when compared to a single-core MLFMA, even for those high aspect ratio objects. Do they put any numbers to those speedups?
They did, and the numbers are pretty convincing. For the FLAM model, running on just a single worker, their method took 140.45 seconds for each MVM iteration. That's matrix vector multiplication, by the way.
Right, right.
The 4-level MLFMA, on the other hand, needed 414.6 seconds per iteration, almost 3 times slower.
Wow, that's a huge difference. And it makes you wonder, if a single core is already that much faster, what kind of speedups could they get by really taking advantage of the parallel nature of their method?
It's a good question. Unfortunately, the paper doesn't give results for multi-core runs on those specific objects, but they do show how the method scales for a large PEX sphere, one with over 1 million unknowns. With 16 workers, they get a speedup of over 12 times compared to a single worker.
Okay, so the potential for massive speed gains through parallelization is definitely there. For those really huge problems, this method could be a game changer.
I think so, especially when you consider that traditional MLFMA can struggle to scale efficiently because of how its hierarchical structure works, all those dependencies between levels. This new method, with its independent boxes, seems much better suited for parallel computing.
Now, we focused a lot on the efficiency, especially for those complex geometries, but they also claim this method addresses the low-frequency breakdown problem that we talked about earlier, the problem that really limits traditional MLFMA. Did they show any evidence for that?
Oh, they did. They went back to that PEX sphere, the one with the diameter of 0.6 meters. But this time, they tested it at a super low frequency, 7.8125 megahertz. This makes the sphere electrically tiny, just lambda 64 in size.
So they deliberately chose a scenario where MLFMA would typically struggle.
Exactly. And to keep things fair, they trained their neural networks specifically at this low frequency. The results are in figure 16, and they're pretty clear. Their method's prediction matches the Mies series solution perfectly. No sign of the breakdown you'd see with MLFMA at those frequencies.
It's amazing that they were able to get that kind of accuracy at such a low frequency, especially with the object being so electrically small. It seems like they've really sidestepped the LFB problem.
It does. And the key to that success is their choice of basis function, that Hertzian dipole. By baking the Hertzian dipole Green's function directly into their machine learning model, they avoid all those numerical issues that pop up in MLFMA at low frequencies.
So they found a really elegant solution to a problem that's been plaguing the field for a while. It seems like we've got a method that's faster, more accurate, especially at low frequencies, and highly parallelizable. Is there anything else? Are there any downsides they point out? Any limitations?
Well, they do mention one limitation, which is that their current implementation isn't hierarchical. We've talked about this a bit. That uniform box structure is fantastic for objects up to a certain size, but it might become less efficient for really electrically large problems. Imagine trying to analyze scattering from a whole aircraft or a complex cityscape using that same box approach.
It's like trying to build a giant complex structure using only one type of Lego brick. Right. At some point, you need more specialized pieces.
That's a good analogy. And they do mention that they are working on introducing some hierarchy into their method, similar to how MLFMA uses multiple levels. The idea is to group boxes together at different levels, creating a tree-like structure for those larger scales.
It makes sense that they need to adapt for those massive problems. But the paper also mentions that introducing this hierarchy might actually affect the strong scalability they've been touting.
Right. When you introduce hierarchy, you inevitably introduce dependencies between calculations. And those dependencies can limit how effectively you can parallelize everything.
So it's a balancing act. They need to find the right level of hierarchy to handle large problems without sacrificing too much of that parallel processing power.
That's exactly it. But even if the strong scalability takes a slight hit, they're confident that their approach will still have a huge advantage over traditional MLFMA, particularly when it comes to load balancing and overall efficiency in a parallel computing environment.
Sounds like there's a lot of exciting research ahead in this area, exploring those hierarchical extensions, fine-tuning the machine learning aspects, and seeing how it performs on even larger and more complex problems.
I agree. This paper really feels like it's laying the groundwork for a new generation of methods for solving electromagnetic scattering problems. It's a testament to what can be achieved when you combine rigorous mathematical modeling with the power of machine learning.
It's been a really fascinating deep dive so far. We've gone through the nitty-gritty details of this new method and explored its strengths and limitations. We've even touched on its potential for future research. But before we wrap up, I'd like to take a step back and think about the broader implications of this work. What does it mean for the future of all those fields that rely on understanding and solving electromagnetic scattering problems? What kind of impact could this have on things like antenna design, radar technology, medical imaging, and beyond?
That's the big question, isn't it? Let's dive into those potential impacts in the final part of our deep dive.
Okay, so we've really dug into the nuts and bolts of this new method. But I'm curious about the bigger picture. How does this research actually impact those fields that depend on solving those electromagnetic scattering problems? Like, what about antenna design? Could this change the game there?
Oh, absolutely. Imagine being able to design and optimize antennas for complex things like aircraft or satellites much faster and with higher accuracy. This method could really push things forward in antenna miniaturization, which would be huge for mobile devices and wearables.
So we're not just talking about small improvements, but maybe even disruptive changes in how antennas are designed and used in all kinds of devices.
Exactly. And it's not just about speed either. Being able to accurately analyze those low-frequency scattering problems could open up completely new possibilities for antenna design, especially for applications that need small antennas operating in those tricky frequency ranges.
That makes sense. And how about radar technology? I imagine this could have a big impact there too.
Yeah. Definitely. Radar systems rely heavily on that accurate scattering analysis to find and track targets. With this new method, we could see more sensitive and robust radar systems. Imagine detecting smaller objects or tracking targets in more difficult environments, all thanks to faster and more accurate calculations.
That would revolutionize a lot of applications, from air traffic control and weather forecasting to things like self-driving cars and even space exploration.
Exactly. And in medical imaging, think about MRI. This method could lead to higher resolution images, faster scan times, maybe even completely new imaging techniques that were too computationally expensive before.
It's amazing to think about the potential in healthcare. Earlier and more accurate diagnoses, more effective treatments, maybe even saving lives. That's powerful stuff.
Absolutely. Using these advancements in computational electromagnetics to actually make a difference in people's lives, that's the ultimate goal.
It's clear that this research has far-reaching implications. But as with any new technology, there are probably some challenges and ethical considerations that need to be addressed as it becomes more widely used.
Oh, definitely. With any powerful tool, you have to think about the ethical side and make sure it's being used responsibly. Like, for example, in radar technology, having more sensitive systems could raise some privacy concerns. We need to have open discussions about these issues and make sure these advancements are used ethically and for the benefit of everyone.
That's an important point. As these technologies become more advanced, we need to keep those conversations going and make sure ethics are at the forefront of how they're developed and used.
I completely agree. It's our shared responsibility to make sure these breakthroughs in computational electromagnetics contribute to a better, more equitable future for everyone.
Well, we've certainly covered a lot of ground in this deep dive. We started with what seemed like a pretty complex research paper, broke down the details, and even explored its potential to transform various fields. As we wrap things up, what are some of the key takeaways you'd like our listeners to remember?
For me, the biggest takeaway is the power of interdisciplinary research. The authors of this paper combined really rigorous mathematical modeling with those cutting-edge machine learning techniques, and the result is something that's both elegant and incredibly practical. It's a great example of what happens when different fields come together to solve challenging problems.
It's a reminder that innovation often happens where those different disciplines intersect, where different perspectives can collide and spark new ideas.
And I hope our listeners appreciate the real-world potential of this new method. We talked about applications in antenna design, radar technology, and medical imaging. But its impact could go far beyond that. It could drive advancements in wireless communication, energy harvesting, remote sensing, really anything that relies on understanding electromagnetic phenomena.
It really feels like a pivotal moment in computational electromagnetics. This research opens up so many possibilities, and I'm excited to see where it leads in the coming years.
Me too. It's been a real pleasure exploring this fascinating topic with you.
The pleasure was all mine. And to all our listeners out there, we encourage you to dive into that paper yourselves, think about the implications, and maybe even contribute to this exciting field of research. Until next time, keep exploring, keep asking questions, and keep on diving deep. All right, get ready for a deep dive, folks. We're taking a look at a paper that says it can solve electromagnetic scattering problems faster than even a 5-level, multi-level fast, multipole algorithm.
Wow.
I know, right? Even just saying that name, multi-level fast, multipole algorithm takes a while.
It does.
So we're talking about the MLFMA, which has been the top dog for figuring out how electromagnetic waves bounce off of all those complex shapes.
Yeah.
But it looks like MLFMA might just have met its match.
Yeah, could be.
This paper we're looking at today, it's all about a new method. It uses machine learning, and get this, it might be able to speed up these calculations and solve a bunch of problems that have been bugging MLFMA for years.
It's a pretty big claim for sure.
Totally, and you know what this means. We're talking about being able to analyze things like planes, satellites, even tiny microchips way faster.
Right.
Faster analysis means faster design, faster development, faster everything for all kinds of tech we use every day.
Absolutely, the applications are huge.
Okay, so let's get down to it. How are they planning to knock MLFMA off its throne?
Well, they're starting by making the problem simpler, which is pretty smart.
Okay, I like where this is going.
Instead of trying to handle this big, complex object all in one go, they break it up into smaller pieces. Boxes, they call them.
Okay, makes sense. Divide and conquer, classic strategy. But how do they represent the electromagnetic activity happening inside each box?
This is where it gets really cool.
Right. I'm listening.
They use these tiny antennas called Hertzian dipoles. They represent the electromagnetic activity inside each box.
Hertzian dipoles. Why those specifically?
Because each one, it has a super simple math representation that makes them really easy to work with, computationally.
I see.
Plus, when you use the same number of these dipoles in each box, you make all the boxes basically twins.
Ah, that's clever. Identical boxes, that means you can process them all at the same time, way more efficiently. No more bottlenecks because every worker is doing the same job.
Exactly. That's the key for scalability. You can throw a ton of computing power at the problem and actually see it get faster. But here's the real magic trick. They use machine learning to predict how these dipoles interact between the different boxes.
Oh, wow. So instead of crunching all those complex calculations between these little antennas the old-fashioned way, they're training a machine learning model to basically learn to speak electromagnetism.
Yeah.
And then they can predict those interactions on its own.
Exactly.
Pretty wild. So how are they training this model?
They've got a two-stage training process. It seems to work pretty well.
Okay, tell me more.
First, they train the model using random data. That helps the network learn the basic connections between how the dipoles are arranged and the electric fields they create.
So it's like teaching the model the basic rules of the game before you let it loose in the real world.
Yeah, exactly. And then they take the model and fine-tune it.
Yeah.
They use data from real electromagnetic simulations of actual objects. That makes the model's predictions super accurate.
Okay, makes sense.
And here's the best part.
What's that?
Once they've got this network all trained up, they can use it on any scattering problem that fits inside what they call the mother box.
Mother box, okay.
Yeah, it doesn't matter what shape the object inside is or what it's made of. They don't have to retrain the model every time they want to use it on something new.
Wow, that's powerful. It's like having a universal translator for all these electromagnetic scattering problems.
It really is. And they actually give several examples in the paper to show how accurate and efficient their method is.
All right, hit me with those examples. What kinds of objects did they test this thing on?
Well, they started with a classic test, a perfectly electrically conducting PIC sphere.
Okay.
And the results were really impressive, not just accurate, but faster than a 5-level MLFMA.
Wow, starting off strong. But a sphere is a pretty basic shape. Did they test it on anything more challenging?
Absolutely. They also tested it on dielectric spheres.
What's special about those?
They're more like real-world materials.
Ah, I see.
And the new method, it still worked really well.
So it can handle different materials, not just perfect conductors. That's good.
Yeah, it is. But I'm sure you're wondering, did they try any really complex shapes? Something with a high aspect ratio, the kind of thing that usually gives traditional methods a hard time.
You read my mind. Did they?
Of course they did. They used two really tough shapes, the flam and the NASA almond.
Okay, I'm not familiar with those.
They're really intricate. They've got sharp edges, curves, the whole works. And the new method handled them like a champ.
That's impressive.
It is. And remember how we talked about MLFMA struggling with those low frequencies?
So did they test this new method on that too?
They did. They tested it on a small sphere at a very low frequency. And you know what? It perfectly matched the analytical solution.
Wow, they really tackled some of those big limitations head on. This is starting to sound like it could really change things.
It seems like it could. Although, to be fair, the authors do acknowledge that there is still room for improvement.
Well, nothing's ever perfect, right? But even so, this speed, this accuracy, how versatile it is, it's really promising. So what does all this mean for the future of electromagnetic analysis, I wonder?
That's a great question. And that's what we're going to talk about in part 2 of our deep dive. This is where things get really interesting.
All right, looking forward to it. All right, let's dive deeper into this. I'm ready to get into the nuts and bolts of how this method actually works.
Okay, sure.
I've talked about the big picture, but now I want to understand the math behind it all.
All right, well, it's basically a 3-stage process.
Okay.
They call it mapping, translation, and inverse mapping.
Mapping, translation, and inverse mapping. Okay. You're going to have to break that down for me.
Okay, so imagine you've got this high-resolution photo and you want to simplify it.
Okay.
Instead of dealing with all the details, you represent it using those Hertzian dipoles we talked about.
Right.
It's kind of like replacing a detailed map with just some markers that show the key areas.
Okay, so we're simplifying things to make them easier to handle computationally. But how do they make sure this simplified version still accurately reflects the original complex current distribution?
That's where they use something called basis functions. Specifically, they start with Rao-Wilton-Glisson basis functions, or RWGs.
RWGs, huh? What are those exactly?
Think of RWGs as the language we use to describe the current flowing on the surface of the object.
Oh,
Each RWG function, it captures the current flowing over a small triangular patch on the surface.
okay. So we've got these RWGs describing the current, but we want to represent it using those simpler Hertzian dipoles. How do they connect those two things?
That's the tricky part of the mapping stage. They need to find the right mix of Hertzian dipoles that accurately create the same electric fields as the original RWG basis functions.
I see. So it's like finding the right set of markers to represent the detailed map.
Exactly. And to do this, they use something called a least squares solution. This method finds the best fit between two sets of data. In this case, they're trying to minimize the difference between the electric fields produced by the actual RWGs and the fields produced by those Hertzian dipoles.
So they're adjusting strengths and orientations of these Hertzian dipoles until the difference in the fields is as small as possible.
Right, but then how do they compare the fields? It's not like they can just stick probes inside the computer, right?
Exactly.
So what they do is they imagine enclosing each box inside a virtual sphere.
Okay.
They pick specific points on this sphere and make sure the electric fields calculated using the RWGs and the Hertzian dipoles are the same at those points.
So if the fields match on this sphere, they'll match everywhere else too.
Exactly. That's thanks to something called the uniqueness theorem.
Wow. So by making sure the fields agree on this virtual sphere, they're basically guaranteeing that the simplified Hertzian dipole representation will give you the same electric field as the original, more complex RWG representation. That's pretty slick.
It is. And to make sure they get a good picture of the electric field on that sphere, they use these special points called spherical Fibonacci lattice points.
Okay.
These points are spread out evenly on the sphere's surface. It's like having sensors all over the sphere.
Gotcha. So we've successfully mapped the complex current onto those simpler Hertzian dipoles. That's stage one done. What's next?
All right, so the next stage is called translation. Now that we've got the simplified representation, we need to figure out how these dipoles talk to each other, across the different boxes.
Right.
They actually present two ways to do this. The first way is called the direct Green's function approach, or DGFA.
DGFA. What's that all about?
It's a very precise method. It uses a mathematical tool called the Green's function to directly calculate the electric field from one dipole at the location of another dipole.
Okay.
It's accurate, but it can take a lot of computing power, especially when you have tons of dipoles.
So it's accurate but slow.
Yeah, and that's where the machine learning approach comes in.
Okay, tell me more.
Instead of calculating each interaction one by one, they train a machine learning model to predict these interactions.
Got it.
It's based on the arrangement of the dipoles.
So the machine learning model acts like a shortcut, letting us quickly figure out the electric field without having to go through the whole DGFA process.
You got it.
Smart. But electromagnetic fields are complex. They have magnitude and phase. How does the model deal with that?
They use a special kind of neural network for this. It's called a complex-valued, fully connected neural network, or CVFCNN for short.
CVFCNN, that's a mouthful.
It is.
But it makes sense to use a network that can work directly with complex numbers. So how do they actually train this CVFCNN?
They use a two-stage process for this as well.
Okay.
First, they train it using random dipole coefficients. This teaches the network the basic relationships between how dipoles are arranged and what electric fields they create.
Like a crash course in electromagnetism 101.
Exactly. Then they refine the model using a more realistic data set, something more like what you'd see with real objects.
So they're tuning it up with real-world data. Makes sense. But hold on, we're not quite done yet, are we?
Right.
We mapped the current to these Hertzian dipoles, and we figured out how they interact. But how do we get back to the actual electric fields?
That's where the final stage comes in, inverse mapping. This stage involves taking the electric field contributions from those Hertzian dipole locations and translating them back to the language of the original RWG basis functions.
So we're going from that simplified representation back to the original, more detailed one.
Exactly. It's like going from the markers back to the full detailed map.
Okay, but how do they do this inverse mapping?
They use another least squares solution, kind of like in that first mapping stage. But this time, they're finding the best coefficients for something called virtual dipoles.
Virtual dipoles. What are those?
They're not real physical dipoles. Think of them as a math tool.
Okay.
They use them to represent the electric field on that virtual sphere we talked about earlier. By finding the right coefficients for these virtual dipoles, they can accurately reconstruct the electric field anywhere inside the box.
So it's like these virtual dipoles are helping us translate the information from the Hertzian dipole world back to our original RWG world.
Exactly. And once they've done that, we can finally calculate the elements of the impedance matrix,
Okay.
which describes how all the basis functions in the problem interact.
It's like we've gone full circle.
Right.
We started with a complex current distribution, simplified it, calculated the interactions, and then brought those results back to the original representation. That's quite a journey. But tell me, how does all this actually play out in real-world situations? What kind of impact could this have on things like antenna design, radar technology, even our understanding of biological systems? All right, we're back for the final part of our deep dive. It's quite a journey. We've gone through all the details of Hertzian dipoles and virtual spheres and complex valued neural networks. So tell me, how does all this math actually translate to real-world stuff? What kind of impact can this method have?
This is the really exciting part. Just imagine being able to design antennas that are way more efficient, radar systems that can find even the stealthiest objects. We might even be able to understand how electromagnetic fields affect biological processes.
Wow. Okay, let's break those down one by one. First up, antenna design. How does this new method change the game for engineers designing antennas?
Well, traditionally, antenna design has been a lot of trial and error.
I bet.
Engineers would design something, simulate it, tweak it, simulate it again, and just keep going until they get what they want.
Yeah.
And this could take forever, especially for complex antennas working at high frequencies.
So this new method, it speeds that whole process up, right? They can try out way more designs in less time.
Exactly. This means engineers can come up with more innovative antenna designs, more efficient antennas for everything from our phones and Wi-Fi to satellites and spacecraft.
That's incredible. Okay, what about radar technology? How does this method impact radar?
Think about trying to detect a stealth aircraft. These aircraft are designed to be invisible to radar, really hard to detect with traditional systems.
So how does this new method help with that?
Well, if you can analyze radar signatures way faster, you can develop radar systems that are much more sophisticated.
I see.
They can detect even the tiniest reflections, and that's huge for national defense and air traffic control.
Okay, that makes sense. Now, the last one you mentioned, biological systems. That one's really interesting to me. How does electromagnetism even play a role in biology?
It's pretty amazing. Our bodies are full of electrical activity.
Really?
Yeah, our nervous system uses electrical impulses to send signals. Our hearts and brains create their own electromagnetic fields.
Wow.
If we could really understand how this all works at the electromagnetic level, who knows what we could learn about how our bodies function.
So you're saying we could potentially use this new method to simulate those electromagnetic interactions, like in the heart of the brain?
Exactly. We could create really accurate virtual models that capture the electrical and magnetic fields. It could change everything about medical diagnostics, how we plan treatments, even drug development.
That's mind-blowing. This is really groundbreaking stuff. It sounds like the combination of machine learning and electromagnetism could revolutionize bioelectromagnetics.
It really could. And honestly, we're only just getting started. Who knows what other problems we'll be able to solve as machine learning gets better and we have more computing power.
It's amazing to think about. If any of our listeners want to check out this research for themselves, where can they find the paper?
It's available online. The title is A Novel, Highly Parallelizable Machine Learning-Based Method for the Fast Solution of Integral Equations for Electromagnetic Scattering Problems.
Awesome. Well, this has been a wild ride. We've gone from complex math to incredible possibilities. This deep dive has really shown me how powerful it can be to combine machine learning and electromagnetism.
It's been great exploring this with you.
And to all our listeners, thanks for joining us on this deep dive. We hope you've learned something new and exciting today, and we'd love for you to subscribe to the deep dive for more fascinating journeys into the world of science and technology. Keep those minds curious and those questions coming. We'll see you next time. Welcome back, everyone. We're diving into a new method for solving electromagnetic scattering problems today. It's a pretty fascinating paper you sent over.
Yeah, it's a good one.
Yeah. A novel, highly parallelizable machine learning-based method for the fast solution of integral equations for electromagnetic scattering problems. And it's proposing to use machine learning to speed things up, but also potentially address the low-frequency breakdown.
Yeah.
Before we dig into the specifics of the new method, can you give us just some background, like what's the current state of solving these scattering problems?
Yeah. So the standard way of solving these problems has been using method of moments,
Okay.
which is often accelerated using techniques like the multi-level fast multipole algorithm, or MLFMA.
Okay.
And MLFMA has been pretty effective, but it does have limitations, especially with low-frequency problem and parallelization.
Yeah.
So imagine you're trying to simulate like a large, complex structure, like an aircraft or a ship at low frequencies. That's where MLFMA can become computationally very expensive.
Yeah.
And dividing the workload effectively across multiple processors can be tricky.
Yeah, that makes sense. So this new method aims to address these limitations. The core idea seems to be this three-stage process: mapping to uniform basis functions, translation using machine learning, and then inverse mapping back to the original problem space.
Right.
What's the rationale behind using these uniform basis functions? And the paper specifies that they're using Hertzian dipoles.
Yeah. So the brilliance of using uniform basis functions is the parallelization potential it offers.
Okay.
By representing the problem in terms of uniformly distributed Hertzian dipoles, the computational workload can be divided very evenly across multiple processors.
Yep.
It's like having a perfectly synchronized team, each member handling a specific, identical portion of the problem.
Okay.
And this leads to very efficient scaling, meaning the computation time decreases proportionally as you add more processors.
Okay.
So you specifically mentioned Hertzian dipoles. So the reason Hertzian dipoles are chosen is because they offer a very simple yet powerful way to represent electromagnetic fields.
Okay.
They are essentially idealized point sources of electromagnetic radiation.
Yeah.
By placing these dipoles uniformly within the simulation space, we can approximate the complex current distributions that exist with surprising accuracy.
Okay.
And this uniformity, like I mentioned, is key to achieving that efficient parallelization.
That makes sense.
Yeah.
So we've mapped the problem onto these uniformly distributed Hertzian dipoles. What's the next step?
So the next step is what they call translation, and this is where the machine learning magic happens.
Okay.
So instead of directly calculating the interactions between dipoles using traditional methods, the researchers trained complex-valued, fully connected neural networks, or CVFCNNs, to predict these interactions.
Okay.
And this is the computationally heavy part, which is traditionally handled by methods like MLFMA, which involve evaluating the Green's function for all dipole pairs. Machine learning essentially provides a shortcut here and significantly speeds up this process.
So walk us through the machine learning part. How do these CVFCNNs actually learn to predict the interactions between dipoles?
Yeah, so the training process is quite ingenious, actually. They employ a two-stage strategy.
Okay.
First, they train the network on a data set of uniformly generated dipole coefficients.
Okay.
This gives the network a broad understanding of the possible input space
Okay.
and the general patterns of how dipole coefficients influence the resulting electric fields. You can think of it as teaching the network the basic grammar of electromagnetic interactions.
So it's like giving the network a crash course in all the possible ways these dipole coefficients can be arranged and how they sort of affect the overall field.
Right, exactly.
Then what's the second stage?
So in the second stage, they fine-tune the network using a more realistic data set. This one's generated by simulating scattering from a Peck sphere.
Okay.
And they randomly assign dipole coefficients within small boxes that kind of move across the sphere's surface. Okay.
So it's essentially capturing snapshots of dipole configurations that the network might encounter in real-world problems. This stage is like giving the network practical experience, fine-tuning its understanding to be more accurate for specific scattering scenarios.
That's a pretty cool approach. You train it on the general principles, and then you refine it using these real-world examples.
Right.
The CVFCNN, it's a complex-valued neural network.
Yeah.
Can you elaborate on that a little bit more?
Sure. So electromagnetic fields have both magnitude and phase, which are represented by complex numbers.
Right.
And unlike traditional neural networks that deal with real-valued inputs and outputs, CVFCNNs are designed to handle these complex numbers directly.
Okay.
This allows them to capture the full complexity of electromagnetic interactions more naturally and accurately. It's like teaching the network to speak the language of electromagnetism fluently.
That's a great analogy.
Yeah.
So now we have these trained networks that can predict the interactions between the dipoles. What's the final step? So the final stage is what they call inverse mapping to subdomain functions.
Okay.
And here we need to translate the results from the dipole world back to the original problem space,
Okay.
which might involve complex basis functions that are specific to the geometry we're analyzing.
So it's like translating from a simplified language back into the original, more nuanced language of the problem.
Exactly.
How do they achieve this inverse mapping?
Right. So they introduced this concept of virtual dipoles.
Okay.
And these are placed at the spherical sampling points where the electric field is calculated. These virtual dipoles are used to represent the electric field inside the test box.
Okay.
And by determining the optimal coefficients for these virtual dipoles, they can then calculate the interaction between the electric field and the original basis functions,
Okay.
effectively completing that inverse mapping.
Fascinating. So we've gone on this sort of round trip, mapping to Hertzian dipoles, leveraging machine learning for fast translation, and then mapping back to the original basis functions. Can you walk us through some of the mathematical underpinnings of these stages?
Sure. So let's start with the representation of the current distribution within each box using those Hertzian dipoles. And equation 3 in the paper nicely encapsulates this. Bar sum bar represents the current distribution at a point bar within the box. This current is essentially the flow of electric charge, which is what generates the electromagnetic fields we're interested in. The equation tells us that this current distribution is made up of a sum of contributions from bar subdomain basis functions, denoted by bar k.
So we're decomposing a complex current flow into a series of simpler components, those
Right.
basis functions.
Exactly.
Okay.
And each basis function has a corresponding coefficient $, which determines its contribution to the overall current distribution. These coefficients are what we're ultimately trying to solve for in our scattering problem.
Okay. This seems to be the standard method of moments formulation for representing the unknown current. How does this relate to the uniform basis functions, the Hertzian dipoles?
Yeah, so that's where the concept of mapping comes into play. Instead of directly working with these potentially complex subdomain basis functions, which might vary from box to box, we introduce a uniform set of basis functions, the Hertzian dipoles.
Right.
And equation 7 describes this. Bar represents the current distribution in terms of the uniform basis functions. It's bar, which are those Hertzian dipoles.
Okay.
2 dies are the coefficients associated with these dipoles.
So we're essentially performing a change of basis, going from the original, possibly complex basis functions to a standardized set of Hertzian dipoles.
Exactly.
What's the advantage of doing this?
So the advantage is twofold. First, as we discussed, it enables very efficient parallelization. By using the same basis functions for all boxes, the computational workload can be divided evenly, allowing for optimal scaling across multiple processors.
Okay.
Second, this mapping process helps us to address the low-frequency breakdown problem.
This is starting to get really interesting. Can you explain how this mapping helps with the low-frequency breakdown issue?
Sure. So the traditional methods for calculating interactions between boxes often rely on approximations of the Green's function that become unstable at low frequencies.
Okay.
This is because those approximations involve expansions that diverge when the box size is electrically small compared to the wavelength.
It's like using a tool that's designed for measuring large objects to try and measure something tiny.
Precisely.
The measurements become unreliable.
Right. But by mapping to uniform basis functions and using machine learning models that are trained on the full Green's function, we can actually bypass those unstable approximations. The machine learning models essentially learn the behavior of the Green's function without relying on those problematic expansions. This makes the method robust even at low frequencies.
That's quite a clever approach. But how do we ensure that the representation using these Hertzian dipoles is accurate? It seems like we're simplifying the problem quite a bit.
Yeah, that's a great question. The accuracy is ensured by carefully choosing the coefficients for the Hertzian dipoles.
Okay.
The mapping process aims to find the optimal set of coefficients, $, so that the electric field produced by the Hertzian dipoles closely matches the electric field produced by the original current distribution.
Okay.
And this is done using a least squares approach.
So we're not just arbitrarily assigning these dipole coefficients. We're finding the best possible values to ensure that the representation remains accurate.
Exactly. And equation 11 in the paper describes this least squares solution, bar wire igloo, where the bar represents the vector of dipole coefficients, Bar represents the electric fields calculated from the original basis functions, and a bard is the matrix describing the contribution of each dipole to the electric field at a set of sampling points.
So we're essentially translating between the language of the original problem with its specific basis functions and the language of those uniform Hertzian dipoles, ensuring that we capture the essential information about the current distribution and the resulting electric fields.
Precisely. And this mapping process is crucial for enabling the use of those powerful machine learning models, which can then calculate the interactions between boxes in a highly efficient and parallelizable way.
This is all incredibly insightful. Before we move on to discuss the specifics of the translation stage and those machine learning models, should we pause here and pick up the mathematical deep dive in the next part?
Yeah, that's a good idea. We can delve into the intricacies of the translation matrix, those complex valued neural networks, and the inverse mapping process in more detail.
Sounds like a plan. We'll be back shortly to continue our exploration of this groundbreaking new method for solving electromagnetic scattering problems. Stay tuned.
Welcome back. We left off discussing the mapping process, which allows us to express those complex current distributions within boxes using those simpler, uniformly placed Hertzian dipoles.
Right, and that simplification really unlocks the efficiency and parallelization.
Yeah.
We've translated our problem into the language of those uniform dipoles. The next challenge is to calculate how these dipoles interact across different boxes. And that's where those machine learning models come in.
Right.
But before we even get to the models, can we walk through the traditional approach, the direct Green's function approach? I think that'll help us really appreciate the elegance of the machine learning solution.
Absolutely. Understanding the direct approach sets the stage for grasping the brilliance of that machine learning strategy. So let's consider two boxes in each other's far zone,
Okay.
labeled I and J, as shown in figure 3 of the paper.
Okay.
And the goal is to calculate the electric field at a point within the test box J.
Okay.
We'll call it point O,
Okay.
due to a dipole at point K within the basis box I.
Okay, so looking at figure 3, I see boxes I and J, and the translation vector between their centers, denoted by AJ.
Okay.
It also shows the locations of the dipoles within each box, a Gannon bar.
Right.
So we want to figure out how the dipole influences the electric field at bar.
Exactly. And equation 12 tells us how to calculate that electric field contribution. Bar B day BB. The term bar D is our dyadic Green's function. It considers the translation between the two boxes, telling us how the electric field propagates from the source dipole at bar B day to the observation point at bar D, factoring in their relative positions and the distance between the boxes.
So we're using the Green's function to map the source dipole's influence onto the observation point's location in the other box.
Precisely, and bar dB is the dipole moment of the source dipole, which describes its strength and orientation.
Okay, that makes sense for a single dipole. But we have many dipoles in each box. How do we manage all those interactions?
That's where equation 13 comes in, generalizing equation 12 for all dipoles within the two boxes. Now, instead of calculating the electric field at a single point $, we're calculating the electric field at all dipole locations within the test box J,
Okay.
due to all dipoles within the basis box I.
Okay.
This is represented by the vector Bartle. Bartle is like a snapshot of the electric field at all the dipole locations in box J caused by the dipoles in box I.
Exactly. And this snapshot is captured by the matrix Bardet,
Okay.
which is called the translation matrix.
Okay.
Each column of this matrix represents the electric field contribution at all test dipole locations in box J due to a single component, X, Y, or Z, of a dipole in box I.
I see how this coming together. We have this translation matrix that captures the interactions between all the dipoles in the two boxes. How do the coefficients of the dipoles factor into the calculations? Good question. So those coefficients are in the vector Barke,
Okay.
representing the excitation of each dipole in the basis box I. We obtained these coefficients during the mapping stage when we found that optimal dipole representation of the original current distribution.
Right. Equation 13 multiplies the translation matrix containing the Green's function information about the dipole interactions with the dipole coefficients, telling us how strongly each dipole contributes to the overall field.
Precisely. And that gives us the electric field at all test dipole locations in box J.
We have calculated the field contribution from one box, but a given box will have multiple boxes in its far zone. How do we account for all those interactions?
Right. So that's where equation 14 comes in. It sums up the contributions from all far zone boxes, where $5 is the set of indices for all boxes in the far zone of box J.
So we're adding up the electric field contributions from all those far zone boxes to get the total electric field at the dipole locations in box day.
Yes. Now, calculating this translation matrix for every pair of boxes seems computationally expensive, and it is.
Right.
That's why the researchers point out a very clever way to exploit symmetry and reduce the number of unique translation matrices we need to calculate.
We can reuse some of these matrices because the dipole configurations and box sizes are identical.
Exactly. This is where that uniformity we emphasized really pays off. Because the boxes are structurally identical, many translation matrices are simply rotated or mirrored versions of each other.
So we don't need to calculate a new matrix for every single box pair. We can use the same matrix with rotations or reflections for many interactions, saving computation time.
Yes. For a system with LL3 meaning 8 cubed or 512 boxes, there are 316 distinct translation vectors.
Okay.
But thanks to symmetry, we only need to calculate 16 unique translation matrices.
Wow.
The rest are obtained through those rotations and reflections.
That's a significant reduction in computational burden. But even with symmetry, calculating these matrices directly using the Green's function is still computationally demanding, especially for large problems.
You're right, and that's where those powerful machine learning models come in, offering a way to speed up this translation stage without sacrificing accuracy.
Okay, I'm ready to dive into those models. How do these machine learning networks emulate those complex Green's function calculations so effectively?
Right, so the work employed here is a complex-valued, fully connected neural network, or CVF-CNN, and these networks are designed to handle complex-valued data, which is essential for representing electromagnetic fields that have both magnitude and phase.
Right, unlike traditional neural networks that just deal with real numbers, these CVF-CNNs can really handle the complexity of those electromagnetic fields.
Precisely. Being fully connected means each neuron in a layer is connected to every neuron in the previous and subsequent layers. And this allows the network to learn very complex relationships between the inputs and outputs.
It's like a densely interconnected web of neurons, each processing and passing information to its neighbors, enabling the network to learn those intricate patterns in those electromagnetic interactions.
A great analogy. So let's look at Figure 5,
Okay.
which shows the structure of the CVF-CNN used in this paper.
Okay.
It consists of an input layer, a hidden layer with H neurons, and an output layer.
Okay, I see the figure. What's being fed into that input layer?
So the input is the normalized dipole coefficients from the basis box I, that vector we discussed earlier.
So we're giving the network information about the strength and orientation of each dipole in the basis box.
Yes. And the output is a prediction of the electric field at the dipole locations in the test box J. In other words, the network is trying to learn the mapping between the dipole coefficients in box I and the resulting electric field in box J.
So the network is mimicking the behavior of that translation matrix,
Right.
capturing all that Green's function information about the dipole interactions.
Precisely. It's learning to approximate the effect of the Green's function without directly evaluating those complex equations.
That's incredible. But how does the network actually learn this mapping? What's the training process like?
So the training process is ingenious. They used a two-stage strategy that combines a uniformly generated dataset with a more realistic dataset based on pseudo-randomly generated surfaces.
Can you break that down? What's the purpose of using those two different data sets?
So the first stage, using uniformly generated data, gives the network a broad understanding of the possible input space. The real and imaginary parts of the dipole coefficients are randomly assigned values between -1 and 1.
So it's like giving the network a crash course in all the different ways those dipole coefficients could be configured.
Exactly. This helps the network learn the general patterns of how dipole coefficients influence the resulting electric fields. However, relying solely on this uniformly generated data might not be enough to achieve the desired accuracy. That's where the second stage comes in.
And that's where that more realistic data set, based on those pseudo-randomly generated surfaces, is used.
Yes. This dataset is generated by simulating a Peck sphere and randomly assigning dipole coefficients within small boxes that move across the sphere's surface.
So it's like taking snapshots of the dipole configurations that the network is likely to encounter in real-world scattering problems.
Precisely. By training on this more realistic dataset, the network fine-tunes its understanding of the dipole interactions and achieves much higher accuracy.
It's like teaching the network the basic rules first, and then showing it examples of actual gameplay to really refine its skills.
A great way to put it. The results of this two-stage training are impressive. The paper reports that the errors achieved by these trained networks are incredibly low, well within the tolerance levels that are typically used in these solvers.
So these machine learning models can hold their own against the traditional direct Green's function approach in accuracy, but also in efficiency.
Absolutely. And the beauty is that once trained, these networks can be reused for various scattering problems as long as the box size and dipole configurations remain the same.
So we're not training a separate network for every new problem. We have this versatile tool that can handle a range of cases.
Exactly. That reusability is a key advantage of the machine learning approach. It significantly reduces the computational overhead compared to recalculating those translation matrices directly for each new problem.
This is all very exciting. How does this method address that low-frequency breakdown problem we discussed earlier?
That's an excellent question. Remember, low-frequency breakdown occurs when traditional methods like MLFMA struggle to accurately calculate the interactions between boxes that are electrically small compared to the wavelength.
Right, those approximations that work well at higher frequencies start to fall apart when you're dealing with those small electrically closed boxes.
Exactly. And the reason those approximations fail is they rely on expansions of the Green's function
Okay.
that become numerically unstable at low frequencies.
So it's like those expansions, which are like simplified versions of the Green's function, start to produce nonsensical results at low frequencies.
Precisely. They're no longer a good representation of the actual physics, and this new method can bypass those unstable expansions by directly evaluating the full Green's function
Okay.
without approximations or using machine learning models that are trained on the full Green's function.
So instead of relying on those shaky expansions, it's using the real deal,
Right.
the full Green's function, which doesn't suffer from those low-frequency instabilities. That's brilliant.
It is, and the paper shows a very striking example of this. They simulated scattering from a Peck sphere at a frequency where the sphere's diameter is only 164th of the wavelength.
Okay.
At this low frequency, the traditional MLFMA method breaks down,
Yeah.
produces inaccurate results.
But the new method using those machine learning models trained on the full Green's function was able to accurately solve the problem.
Exactly. Their results perfectly matched the analytical solution, demonstrating its resilience against low-frequency breakdown.
This is groundbreaking. It seems like this method could unlock a whole new realm of electromagnetic problems that were previously just out of reach.
I completely agree. And the authors are already exploring ways to extend this method to a multi-level hierarchical structure,
Okay.
similar to how MLFMA was developed as an extension of the fast multipole method.
So they're taking inspiration from the successes of MLFMA, but incorporating this new machine learning twist to overcome its limitations.
Precisely. By combining the best of both worlds, they're paving the way for even faster and more accurate solutions to those challenging electromagnetic scattering problems.
This has been an incredible deep dive into the world of electromagnetism and the power of machine learning. We've explored the mathematical foundations, the clever use of machine learning, and those ingenious strategies for handling those computationally demanding calculations. It's clear that this research has the potential to revolutionize a wide range of fields that rely on solving electromagnetic scattering problems. I'm realizing, though, we're pushing the limits of this segment's length again. Perhaps we should pause here and continue our exploration in the next part.
A great idea. We can delve into the details of the inverse mapping stage and explore the broader implications of this research for various fields.
Sounds like a plan. We'll be back shortly to wrap up our journey into this groundbreaking new method for solving electromagnetic scattering problems. Stay with us. Welcome back to our deep dive into the world of electromagnetic scattering. We've covered a lot of ground from the traditional method of moments and its limitations to the ingenious use of uniform basis functions and machine learning to accelerate calculations and address low-frequency breakdown. Before we wrap up, let's take a closer look at that final stage of this process, the inverse mapping to subdomain functions.
Right.
We've seen how the machine learning model predicts the electric fields at those dipole locations.
Right.
But how do we translate those predictions back into a solution for the original problem?
That's a key question. Our ultimate goal is to find the interactions between the original basis functions, not just those auxiliary Hertzian dipoles we introduced for computational efficiency. This inverse mapping stage is what bridges that gap.
So it's like we took a detour into the world of dipoles for faster calculations, and now we need to find our way back to the original route.
Exactly. And the paper presents a very elegant way to do this. Figure 4 illustrates the inverse mapping concept. Could you take a look at that?
Okay, I see figure 4. It shows the test box J and the spherical sampling points where we calculated the electric fields using the machine learning model. I also see these virtual dipoles at those sampling points. What are those for?
Those virtual dipoles are crucial for mapping the electric field information from the dipole locations back to the original subdomain basis functions. We essentially represent the electric field inside the test box as a sum of contributions from these virtual dipoles, each having an unknown coefficient that we need to determine.
So it's like how we use the Hertzian dipoles to represent the current distribution,
Right.
but now we're using virtual dipoles to represent the electric field itself.
Precisely. Equation 15 captures this mathematically. Bark Doral d by sum, bar Vs bar VL, der Vm1, bar VL is the electric field at a point inside the test box due to those virtual dipoles.
Okay, I see the Green's function again. Barbara describing how the field propagates from each virtual dipole at BARD. And I'm guessing bar represents each virtual dipole's dipole moment.
You're absolutely right. And those Tolliver values are the unknown coefficients we need to find. They determine each virtual dipole's contribution to the total electric field.
Got it. So this equation describes the electric field inside the box using virtual dipoles and their coefficients. But how do we actually determine those coefficients? We don't know the exact electric field inside the box, do we?
That's where the beauty of this method lies. We already know the electric field at those specific sampling points on the spherical surface thanks to our machine learning model. Remember, it gave us the predicted electric field at those dipole locations.
You're right. So we can use that information from the machine learning model to find the best fit values for those virtual dipole coefficients, $.
Exactly. We use a least squares approach as shown in equation 16. Text argument of ovals, and there's also a text argument critic oval. This equation aims to minimize the difference between the predicted electric field occurs and the electric field produced by those virtual dipoles over the day.
So we're essentially finding the set of virtual dipole coefficients that create an electric field, matching the predictions from our machine learning model as closely as possible.
Precisely. And equation 17 provides the solution. Bar Q, $. This equation gives us the best values for those virtual dipole coefficients represented by the vector occurs.
Okay, so we've used those machine learning predictions to determine the coefficients for those virtual dipoles. What's the next step? How do we use those virtual dipoles to calculate the interactions with the original basis functions?
We can now use equation 15 again, but this time we evaluate it at any point inside the test box, including the points where those original subdomain basis functions are defined.
So we're using those virtual dipoles to essentially interpolate the electric field from the sampling points to any point within the box, including the points where our original basis functions are located.
Exactly. This allows us to calculate the interaction between the electric field and the original basis functions, completing that inverse mapping process.
This is really clever. By introducing these virtual dipoles and using the machine learning predictions to figure out their coefficients, we found a seamless way to connect the world of dipoles back to our original problem.
I couldn't agree more. And this inverse mapping is what ultimately lets us assemble the complete picture of the electromagnetic interactions within our system, enabling us to solve those scattering problems with remarkable efficiency and accuracy.
This has been a fascinating deep dive into a truly groundbreaking method. We've explored the mathematical foundations, the clever use of machine learning, and those ingenious strategies for handling the computationally demanding calculations. It's clear that this research has the potential to revolutionize many fields that rely on solving electromagnetic scattering problems.
I completely agree. The possibilities are vast. Imagine the advancements in antenna design, radar technology, medical imaging, even fundamental physics research.
It's amazing to think that this method could lead to breakthroughs in so many areas. What are some of the most exciting potential applications you see on the horizon?
I think the potential for designing highly efficient antennas for next-generation communication networks is particularly exciting. Imagine antennas for 6G or even 7G that are 10 times more efficient than current designs, enabling faster data transfer rates and wider coverage.
That would be a game changer for wireless communication. And what about medical imaging? Could this method lead to more sensitive and accurate diagnostic tools?
Absolutely. With this method, we could simulate the interaction of electromagnetic waves with biological tissues at unprecedented detail, potentially enabling the early detection of tumors or other abnormalities that are currently difficult to image.
Wow, those are some incredible possibilities. It sounds like this research could truly have a profound impact on technology and healthcare.
And let's not forget the impact this could have on our understanding of fundamental physics. By accurately simulating the interaction of light with matter at various frequencies, we could gain new insights into quantum electrodynamics and perhaps even uncover new physics beyond the standard model.
That's a truly inspiring thought. It's amazing to think that a method rooted in computational electromagnetism could have such far-reaching implications.
It really speaks to the power of human ingenuity and the transformative potential of combining cutting-edge techniques from different disciplines.
Well said. This has been an incredible journey through the world of electromagnetic scattering and machine learning. Thanks for joining me on this deep dive.
Thank you for having me. It's been a pleasure discussing this groundbreaking research with you.
And thank you, listener, for joining us on this deep dive. We hope you've enjoyed exploring the intricacies of this fascinating new method and are as excited as we are about its potential to shape the future of science and technology. Until next time, keep those minds curious. Welcome back to the deep dive. You guys sent us a preprint research paper, and we're going to take a deep dive into it. It's a fascinating one all about how machine learning can be applied to solve electromagnetic scattering problems, specifically using a novel method that's highly parallelizable.
Yeah.
Sounds pretty intense.
Yeah, it is, but also incredibly exciting. This paper is tackling the challenge of making these computationally intensive simulations much faster and much more efficient.
Okay, so before we jump into the nitty-gritty of their method, can you remind us why solving these electromagnetic scattering problems is so important in the first place?
Sure. Understanding how electromagnetic waves scatter is fundamental to a wide range of technologies. Think about antennas.
Okay.
Designing antennas efficiently relies on knowing how they'll radiate energy into their surroundings. The same goes for radar systems, which use scattering to detect and locate objects.
Right.
Even medical imaging techniques like MRI exploit the principles of electromagnetic scattering.
So it's really a foundational concept with far-reaching applications. But as you mentioned, these calculations can become quite complex, especially for large or intricate structures.
Exactly. Traditional methods for solving these problems often involve solving integral equations, which can be computationally very demanding, especially when dealing with objects that are large compared to the wavelength of the electromagnetic wave, or when you need very high accuracy in your simulations.
Okay, so that's where machine learning enters the picture.
Precisely. This research paper proposes using machine learning to significantly accelerate the solution of these integral equations. They've developed a method that leverages neural networks to predict key electromagnetic interactions, making the whole simulation process much faster.
That sounds incredibly promising. Can we delve into the specifics of their method? They keep mentioning a group-by-group interaction scheme. What's that all about?
Yeah, so it's a clever three-step process that forms the backbone of their approach. First, they simplify the complex geometry of the problem by representing it using a collection of small boxes. Within each box, they use a fixed number of Hertzian dipoles to represent the electromagnetic behavior. This is the mapping stage.
Hertzian dipoles. Could you remind us what those are and why they're important in this context?
Of course. Hertzian dipoles are essentially tiny idealized antennas, the simplest radiating elements you can have. They emit electromagnetic waves in a very predictable pattern. By strategically placing a grid of these dipoles within each box, they create a simplified representation of the original structure's current distribution.
Okay, so they're using these dipoles as building blocks to represent the more complex electromagnetic behavior of the original object.
Yes.
I'm starting to see how this simplification might help. What happens next?
The next step is where the machine learning magic comes in.
Okay.
This is the translation stage. They use pre-trained neural networks to predict how these dipoles interact with each other across different boxes. Instead of calculating each interaction individually using traditional computationally intensive methods, the neural networks can predict these interactions much faster.
So the neural network is essentially learning the physics of how those dipoles interact and then using that knowledge to predict the interactions in new scenarios.
That's exactly right.
Interesting.
And the type of neural network they use is called a complex-valued, fully connected neural network, or CVFCNN for short. These networks are specifically designed to handle the complex numbers that are inherent in electromagnetic wave calculations.
I see. So they've simplified the problem representation and then trained a specialized neural network to handle the interactions between those simplified elements.
Exactly.
That's clever. What about the final step?
The final stage is called inverse mapping.
Okay.
This is where they take those predicted dipole interactions from the translation stage and translate them back to the original, more complex geometry.
Mm-hmm.
This provides information about the overall electromagnetic behavior of the structure, which is what we're ultimately interested in.
So they've essentially gone full circle.
Yeah.
They started with the complex structure, simplified it to make it manageable for the machine learning model, used the model to predict interactions, and then translated those results back to the original structure.
Yeah.
That's quite an elegant approach.
It is, and it's surprisingly effective, as their numerical examples demonstrate.
Speaking of those examples, I'm eager to see how this method performs in practice.
Yeah.
But before we get to that, I'd love to delve a bit deeper into the mathematical details of each stage.
Sure.
Let's start with the mapping stage. How do they mathematically represent those Hertzian dipoles and their connection to the original basis functions used to describe the current distribution?
Excellent point.
Yeah.
Let's unpack the math behind the mapping stage.
Okay.
They begin by expressing the current density within a box using the original subdomain basis functions.
Okay.
This is shown in equation 3 of the paper.
Okay.
E equals the sum over n of an n times phin.
Mm.
Here, JR represents the current density at a point R inside the box.
Yeah.
And are the coefficients representing the contribution of each basis function.
Okay.
And phin R are the basis functions themselves.
So this equation is essentially setting the stage by defining the current distribution using those original basis functions, which I assume are something like the Rao-Wilton-Glisson or RWG basis functions commonly used in computational electromagnetics.
Yes, you're absolutely right.
Okay.
RWG basis functions are a popular choice for representing surface currents on objects in these types of simulations.
Yeah.
They have some nice mathematical properties that make them well suited for this task.
Okay, so equation 3 establishes the current distribution using these basis functions.
Yeah.
What's the next step in connecting this to the Hertzian dipoles?
The next step involves calculating the electric field produced by this original current distribution.
Okay.
This is where the dyadic Green's function comes in. Equation 4 expresses the electric field, EO, as EOR, equals the integral over V prime of GOPR times GOR.
Okay.
In this equation, GRR is the dyadic Green's function, which relates the current at a source point R to the electric field it produces at an observation point R.
Okay.
The integral is performed over the volume of the box, summing up the contributions from all the tiny current elements within the box.
So the dyadic Green's function is essentially a mathematical tool that describes how the electric field propagates from a current source to a specific point in space.
Exactly. And it's a key component in linking the original current distribution to the electric field it produces, which is ultimately what we're interested in understanding.
Now, how do those Hertzian dipoles enter the picture? Where do they fit into this mathematical framework?
Well, remember that the goal is to represent the complex current distribution within each box using a simplified set of Hertzian dipoles. To do this, they introduce a new set of basis functions, which they call uniform basis functions.
Okay.
These uniform basis functions represent those strategically placed Hertzian dipoles within the box.
Okay.
Equation 7 defines the current distribution, Ju, for these dipoles. Ju equals the sum over k of Ju times delta minus PdK. Here, ICART represents the unknown coefficient for each dipole.
Right.
PdK represents the position of the kth dipole.
Okay.
And delta, or PdK, is the Dirac delta function, which essentially ensures that the current is concentrated at the dipole locations.
Okay, so this equation is similar in structure to equation 3, but instead of using those RWG basis functions, they're now using these delta functions to represent the point-like nature of the Hertzian dipoles.
Precisely. And the goal is to find the optimal values for those C coefficients, the dipole strengths that best replicate the electric field produced by the original, more complex current distribution.
So it's like finding the perfect combination of dipole strengths and positions to mimic the electromagnetic behavior of the original structure within that box.
Exactly. They do this by minimizing the difference between the electric field produced by the original current distribution, EO, and the electric field produced by the dipoles, UU. This minimization is done over a spherical surface that encloses the box. Equation 9 sets up this optimization problem. Minimize the sum over I of the absolute value of EORI minus URI, all squared.
Okay.
This equation represents the sum of the squared differences between the two electric fields at a set of sampling points, ARI, on the spherical surface.
Okay, so they're essentially trying to find the dipole arrangement that produces the closest match to the original electric field at those specific points on the sphere.
Exactly. And to make this computationally tractable, they discretize this integral by choosing a finite number of sampling points and turn it into a matrix equation.
Okay.
This is shown in equation 10. The norm of B minus AC all squared equals mana.
Okay.
Here, B is a vector containing the electric field values at those sampling points due to the original basis functions. A is a matrix that captures the relationship between the dipole moments and the electric fields they produce at those sampling points.
Right.
And C is the vector of unknown dipole coefficients.
So this matrix equation represents a compact way of expressing that optimization problem they set up in equation 9. And the goal is to find the values of C.
Yes.
The dipole coefficients.
Yes.
That minimize the difference between the two electric fields.
Precisely.
Right.
And they solve this matrix equation using the pseudo-inverse of A, denoted as A. Equation 11 gives the solution. C equals A times B.
Okay.
This gives us the optimal set of dipole coefficients that best represent the original current distribution within that box.
So they've effectively mapped the complex current distribution represented by those RWG basis functions onto a simpler set of Hertzian dipoles, capturing the essential electromagnetic behavior within that box.
Yes.
It's like creating a condensed version of the electromagnetic information.
That's a great way to put it. And the beauty of this approach is that once they've calculated these dipole coefficients for a given box size, they can store them and reuse them for any object that fits within that same box. This saves a significant amount of computation time, especially when simulating multiple objects or objects with repetitive structures.
That makes a lot of sense. So they've cleverly simplified the problem representation, but the real test is how accurately this simplified model captures the interactions between different boxes.
Yeah.
This brings us to the translation stage and the role of those machine learning models.
Yeah.
Let's dive into the math behind that stage in part 2.
Absolutely. That's where things get even more interesting.
I can't wait.
So picking up where we left off, let's move on to the translation stage where those machine learning models come into play.
Perfect. We've talked about how they simplify the representation of the structure using these dipole moments within boxes, but now we need to understand how they actually calculate the interactions between these boxes.
Yeah, that's right. The translation stage focuses specifically on calculating the electromagnetic interactions between dipoles that are located in different boxes, particularly those that are far apart from each other.
And I imagine those interactions are crucial for accurately capturing the overall scattering behavior, right?
Absolutely. If we only considered the interactions between dipoles within the same box, we'd be missing a big part of the picture. Those long-range interactions where the electric fields are weaker contribute significantly to the overall scattering pattern.
That makes sense, but I'm guessing those long-range interactions are also more computationally challenging to calculate.
You're exactly right. Traditional methods often struggle with these far zone interactions, especially when high accuracy is needed. That's where the machine learning models come in. They've been trained to predict those far zone interactions accurately and efficiently.
Okay, so they're essentially outsourcing those tricky calculations to a neural network that's learned how to handle them. Let's break down how this prediction process works mathematically, starting with equation 12 in the paper.
Great idea. Equation 12 is the starting point for understanding how they predict those dipole-to-dipole interactions. It describes the electric field, E, at a specific dipole location in the test box due to a dipole in the basis box.
So it's calculating the field contribution from one dipole in a box to another dipole in a different box, right?
Exactly. And they use the dyadic Green's function, again, denoted by D in the equation, to describe how the field from the basis dipole propagates to the test dipole location. It also includes the dipole moments of both the basis dipole idle and the test dipole EDK, as well as their positions relative to each other.
I'm seeing those position vectors, RDL and RDK, in the equation as well. So they're taking into account both the strength of the dipoles and their relative locations in space.
Precisely. And they've also included another position vector, which represents the relative position between the two boxes themselves. So they're considering the positions of the dipoles within their respective boxes, as well as the relative positions of the boxes themselves.
That's a lot of positional information to keep track of. I'm assuming they need all of that to accurately model the electromagnetic interactions.
They do. Remember, electromagnetic fields depend not only on the strength of the sources, but also on their relative distances and orientations. So all these position vectors are essential for capturing those spatial relationships accurately.
Okay, so equation 12 describes the interaction between a single pair of dipoles. But we need to account for all the dipole interactions between two boxes, right? Is that where equation 13 comes in?
Exactly. Equation 13 generalizes equation 12. To handle all the dipole interactions between the two boxes simultaneously, it's a matrix equation that expresses the electric field at all the test dipoles due to all the basis dipoles.
So instead of calculating each interaction individually, they're doing it all at once using matrix operations. That seems much more efficient.
It is. And they introduce a new matrix in this equation, GUIJ, which they call the translation matrix.
What exactly does this translation matrix represent? What information does it contain?
The translation matrix essentially encodes all those dipole-to-dipole interactions we've been discussing. Each element of this matrix corresponds to the electric field contribution from a specific basis dipole to a specific test dipole, taking into account their positions and orientations.
So it's like a compact lookup table that tells you how each dipole in one box influences every other dipole in the other box.
That's a great way to think about it. And here's where the computational challenge arises. Calculating this translation matrix directly can be very time-consuming, especially when you have many dipoles and many box-to-box interactions to consider.
Oh, I see. So they're facing the same problem we discussed earlier. Traditional methods are just too computationally expensive for these types of calculations, especially when you're dealing with large, complex structures.
Exactly. And this is where their clever use of machine learning really shines. Instead of directly calculating each element of that translation matrix, they use those pre-trained CVF-CNNs to predict the entire matrix at once.
So they're using the neural network to essentially bypass those time-consuming calculations, replacing them with a much faster prediction step that's an incredibly clever application of machine learning.
It is. And they've carefully designed and trained these networks to ensure that their predictions are remarkably accurate, as they demonstrate in their numerical examples.
This is fascinating. I'm starting to see the power of combining these fundamental electromagnetic principles with the predictive capabilities of machine learning. It's like they're teaching a computer to understand and predict the physics of how electromagnetic waves interact with complex structures.
I agree. It's a beautiful example of how these two fields can complement each other to solve challenging problems.
Now, before we move on to the final stage, the inverse mapping, I'd love to understand a bit more about how they train those CVF-FCNs they mentioned using rotational and mirror symmetries to streamline the training process. Can you explain how that works?
Absolutely. That's another example of their clever approach to problem solving, because they're representing the structure using a regular grid of identical boxes. There's a lot of inherent symmetry in the problem.
Right, so many of the box-to-box interactions are essentially the same, just rotated or reflected in space.
Exactly. And they exploit those symmetries to significantly reduce the amount of training data they need for those neural networks.
That makes sense. So instead of training separate networks for every possible box-to-box configuration, they can group together those interactions that are equivalent through symmetry and use a single network to handle them all.
Precisely. This reduces the computational cost of training those models and makes the overall method even more efficient.
It's like recognizing that a square looks the same, whether you rotate it by 90 degrees or flip it across a diagonal. You don't need to relearn everything from scratch each time you encounter a slightly different orientation.
That's a great analogy. They're essentially teaching the neural network to recognize those fundamental patterns and symmetries in the problem, which allows it to generalize its knowledge to a wider range of scenarios.
This is all starting to come together. They've simplified the problem representation, used machine learning to predict those crucial far zone interactions, and exploited symmetries to make the training process more efficient. It's a very well thought out approach.
I agree. They've clearly put a lot of thought into making this method as efficient and accurate as possible.
Okay, so we've mapped the original structure to a dipole representation, used machine learning to predict those dipole interactions, and taken advantage of symmetries to make the training process more efficient. What's next? How do they bring all this information back to the original, more complex geometry in the inverse mapping stage?
That's the final piece of the puzzle, and it's just as ingenious as the previous steps. Let's delve into the mathematics of the inverse mapping stage in part 3.
Okay, so we've made it to the final stage. The inverse mapping, it feels like we've been on quite a journey. We started with this complex scattering problem, simplified it by representing the structure using dipole moments within boxes, used machine learning to predict the interactions between those dipoles, and even exploited symmetries to make the training process more efficient. Now it's time to bring it all back home and relate those predicted dipole interactions back to the original, more complex geometry. That's what this inverse mapping stage is all about, right?
Exactly. The inverse mapping stage takes those predicted dipole interactions and cleverly translates them back into information about the original structure. We've essentially solved the problem in this simplified dipole representation, and now we need to decode those results to understand what's happening in the real world.
I love that analogy of decoding. It's like we've translated a complex message into a simpler code, transmitted it efficiently, and now we need to translate it back to understand the original meaning. So how do they actually perform this decoding? What's the mathematical recipe for this inverse mapping step?
They use another clever trick involving those virtual dipoles we discussed earlier, remember? Those are strategically placed dipoles on a spherical surface surrounding each box they were introduced in the mapping stage to help minimize the difference between the electric fields produced by the original basis functions and the simplified dipole representation.
Right. They use those virtual dipoles to ensure that the dipole representation accurately captured the electromagnetic behavior of the original structure within each box.
Precisely. And in this inverse mapping stage, they use those same virtual dipoles, but for a different purpose this time, they want to find the optimal dipole moments for these virtual dipoles that would produce the same electric field as the predicted dipole interactions from the translation stage.
Okay, so it's like a reverse engineering process.
Yeah.
They know what the electric field should be at those virtual dipole locations based on the machine learning predictions from the translation stage, and they're working backward to find the dipole moments that would create that field.
Exactly. They're essentially using those virtual dipoles as probes to sample the electric field and then inferring what's happening within the box based on those measurements. Equation 15 in the paper expresses the electric field EV'd produced by these virtual dipoles.
It looks very similar and structured to equation 8, which described the field produced by the uniform basis functions within the box.
You're right. It uses the same dyadic Green's function, D, to describe the field propagation from those virtual dipoles, and it has a new set of unknown coefficients, QL, which represent the dipole moments they're trying to find.
So they're essentially reusing the same mathematical framework, but with a different set of unknowns and a different goal in mind.
Precisely. And their goal is to find the values of those QL coefficients, the virtual dipole moments that produce an electric field that matches the field predicted by the machine learning networks during the translation stage equation. 16 sets up this matching condition as a least squares optimization problem.
I'm seeing that equation 16 defines the error as the difference between the predicted electric field, EJ, from the translation stage, and the field produced by those virtual dipoles, EV'd. They want to find the values of QL that minimize this error.
Exactly. And just like in the mapping stage, they solve this optimization problem using the pseudo-inverse of a matrix equation 17, which is the solution. Q equals AEJ.
Okay.
Here, Q is the vector of optimal virtual dipole moments. A is the pseudo-inverse of the matrix that relates those virtual dipole moments to the electric field they produce at the sampling points. And EJ is the vector of predicted electric field values from the translation stage.
So they've used those predicted electric field values to determine the optimal dipole moments for the virtual dipoles surrounding the box. But how does this information about the virtual dipoles tell us anything about the original, more complex structure within the box?
That's a great question. Remember that those virtual dipoles were carefully chosen to be located outside the box on that spherical surface. This means that the electric field they produce at those locations depends on the overall electromagnetic behavior of everything inside the box, including the original structure they're trying to analyze.
Ah, I see. So by finding the virtual dipole moments that match the predicted electric field, they're indirectly learning something about the original current distribution within the box.
Exactly. They're essentially extracting information about the original structure by observing its electromagnetic signature from the outside. It's a bit like figuring out what's inside a closed box by shaking it and listening to the sounds it makes.
That's a fantastic analogy. So they've essentially gone full circle. They started with the original basis functions, mapped them to a dipole representation, use machine learning to predict the dipole interactions, and then use those predictions to indirectly infer the electric field back at the original test function locations. It's a remarkably indirect but clever way to solve the problem.
I agree. And it's a testament to their deep understanding of both electromagnetism and the capabilities of machine learning. They've managed to combine these two fields in a way that's both elegant and incredibly effective.
And as they've shown in their numerical examples, it works beautifully in practice. They've achieved significant speedups compared to traditional methods while maintaining high accuracy.
Absolutely. Their results are very impressive, and they highlight the potential of this method to revolutionize how we approach electromagnetic simulations.
Now, before we wrap up this deep dive, I want to touch on one more thing. They emphasize the parallelization aspect of their method. How does this group-by-group interaction scheme lend itself so well to parallel computing? It seems like an inherently sequential process with all these different stages.
That's a great point. While the overall workflow has these distinct stages, the beauty of their method lies in how they've structured the calculations within each stage. The key to their parallelization success is the fact that once they've mapped everything to those uniform dipole representations, the interactions between different boxes become completely independent.
Right, because they're treating each box as a self-contained unit,
Hmm.
with those dipoles capturing all the relevant electromagnetic information within that box.
Exactly. This means that you can calculate those box-to-box interactions simultaneously on different processors or computer cores without any need for communication or data sharing between them. This is what gives them that remarkable strong scalability they discussed in the paper.
So it's like having a team of workers, each with their own set of tools and instructions, all working independently on different parts of a larger project. And as they add more workers, they can complete the project faster without any bottlenecks or coordination overhead.
That's a perfect analogy. And as they demonstrated in their scalability tests, the computation time decreases almost linearly as they add more processors. This is a clear indication that their parallelization scheme is highly efficient and can take full advantage of modern parallel computing architectures.
So they've created a method that's not only accurate, efficient, and avoids those low-frequency breakdown issues, but also scales beautifully on parallel computing platforms. It's truly a game changer for the field of electromagnetic simulations.
I wholeheartedly agree. It's an exciting time to be working in this field, and I can't wait to see how this research evolves in the coming years.
Me too. And for our listener who's been on this incredible journey with us, we hope you've gained a deeper appreciation for the power and beauty of combining machine learning with fundamental physics to tackle complex problems. It's a testament to the ingenuity of these researchers and the incredible potential of interdisciplinary collaboration.
It's been a pleasure sharing these insights with you. We encourage you to explore the full research paper if you're eager to dive even deeper into the mathematical details and nuances of their approach.
That's a great suggestion. And remember, folks, the world of science and technology is constantly evolving, with new discoveries and breakthroughs happening all the time. So stay curious, keep learning, and join us again on our next deep dive into the fascinating world of cutting-edge research. Welcome back to the deep dive. Ready to dive into another fascinating paper?
Absolutely. Always excited to see what's new and groundbreaking.
Well, let's get right to it. Today's paper is called, and get ready for this mouthful, A Novel Highly Parallelizable Machine Learning-Based Method for the Fast Solution of Integral Equations for Electromagnetic Scattering Problems.
Quite a title, but it sounds like they're tackling a really important problem.
They are. The paper basically proposes using machine learning to make electromagnetic simulations way faster and more efficient, especially for complex shapes and at low frequencies, which are notoriously tricky.
Yeah, traditional methods like MLFMA can really bog down in those situations. So using machine learning is a pretty radical idea.
It is, and their approach is really clever. They use this three-stage process, they call it mapping, translation, and inverse mapping, to basically train a neural network to predict how electromagnetic waves scatter off an object.
Okay, I'm intrigued. Break that down for me a bit. What's going on in each of those stages?
Sure. So imagine you're trying to simulate, let's say, an antenna, which has a pretty complex shape. The first step, mapping, is to represent this complex shape using a bunch of tiny antennas called Hertzian dipoles.
Ah, so you're kind of breaking down the complexity into smaller, more manageable elements.
Exactly. These dipoles are like the building blocks for the simulation. Now, the translation stage, this is where the machine learning magic comes in. They train this special type of neural network, a complex valued neural network, to predict how the fields from one group of dipoles will interact with another group.
Wait, so the neural network is actually learning the physics of how these waves interact.
You got it. It's learning the underlying rules of how these waves behave. And it does this by being trained on tons of data, all based on something called the Hertzian dipoles Green's function, which describes how the fields from a single dipole spread out in space.
That's pretty mind-blowing. So the neural network essentially bypasses all the complex calculations that traditional methods have to crunch through.
Yep, and that's what makes it so efficient. Once the neural network is trained, it can predict these interactions much faster than traditional methods ever could.
I can see where this is going. So after the mapping and translation stages, what happens in the inverse mapping?
Okay, so now we have these predictions from the neural network about how the fields are interacting. The inverse mapping stage translates these predictions back into the language of our original problem. So basically, it gives us the final solution for how the electromagnetic waves scatter off that original complex object.
So the neural network is like this super efficient shortcut for solving a really complicated problem.
Precisely. Okay, so that's the basic idea. But the big question is, how accurate is it? Can it really compete with those tried and true traditional methods?
Well, that's what's so exciting about this research. They tested their method on all kinds of objects, simple spheres, more complex shapes like the Peck flam, and even the NASA almond model. And the results are amazing.
You tell. Give me the juicy details.
Well, their method showed excellent agreement with both traditional MLFMA simulations and analytical solutions, which are considered the gold standard for accuracy. Basically, it can capture the complex behavior of these waves with a very high degree of precision.
So it gets an A+ for accuracy. But how about speed? How does it stack up against those traditional methods?
Well, that depends on a few things, like the complexity of the object and the frequency range you're dealing with. For simple shapes, it was slightly faster than MLFMA, even on a single processor. But when you get to those more complex shapes, like the flam and almond models, that's where this method really takes off.
Really? How much faster are we talking?
Significantly faster, even on a single processor. And remember, those complex shapes are the ones that really make traditional methods struggle.
Wow, so it's not just a marginal improvement, it's a huge leap forward. What makes it so much faster for those tricky shapes?
It's all about how it approaches the problem. Traditional MLFMA uses this hierarchical structure, which can get bogged down when you're dealing with objects that have a high aspect ratio, meaning they're long and thin, like the flam and almond models.
Got it. So it's like trying to fit a square peg in a round hole.
Exactly. This new method, though, it doesn't rely on that same structure. It leverages the symmetry of the problem, so it stays efficient even with high aspect ratio objects.
Okay, that makes sense. But what about that low-frequency breakdown issue that we talked about earlier? Can this method actually handle those situations where traditional methods just fall apart?
That's another area where it really shines. They tested it on a sphere at a super low frequency, where traditional MLFMA is basically useless. And guess what? Their method produced accurate results, perfectly matching the analytical solution.
No way. So it's not just faster and more versatile, it's also more robust and reliable in those challenging low-frequency situations.
This is seriously impressive.
I know, right? This research is really shaking things up in computational electromagnetics. All right, before we get into all the nitty-gritty details about the machine learning architecture and how they trained it, let's just pause for a second and let our listeners soak this all in.
Yeah, it's a lot to take in, for sure.
We've basically just outlined a method that could completely change how we approach electromagnetic simulations. Faster, more efficient, more reliable, especially for those really tough problems that have always been a headache.
It's truly groundbreaking research.
Okay, now that we've got a good handle on the overall approach and its potential, let's dive into the heart of it, the machine learning. What kind of neural network are we talking about here?
They used a pretty straightforward architecture, actually. A feed-forward, fully connected neural network with just one hidden layer. But there's a twist. These neural networks work with complex numbers, not just real numbers.
Complex numbers, huh? Remind us why those are so important when we're talking about electromagnetic waves.
Right, because electromagnetic waves aren't just about strength. They also have a phase, kind of like the timing of a wave. And complex numbers are perfect for representing both the magnitude and the phase of these waves.
Right, the phase. It's not just how strong the wave is, but where it is in its cycle, right?
Exactly. And to deal with that, this neural network uses complex valued weights and biases. They went with a single hidden layer with a dimension of 50. Now, the training process is pretty interesting. It's a two-stage approach.
2 stages. Why do they need that?
Well, you wouldn't throw someone who's never swum before straight into the ocean, right? You'd start them off in a pool, teach them the basics. It's kind of the same idea here. The 2 stages make sure the neural network is ready to tackle real-world problems.
So like a neural network boot camp.
Exactly. The first stage uses a very general data set where they just randomly assign values, both real and imaginary, to the coefficients of each dipole. This makes sure the network sees all sorts of different configurations. They train it until the error between its predictions and the actual field interactions is less than 10 to 3.
That's a really tiny margin of error.
It is. So stage 1 is about building a solid foundation of knowledge. Then comes stage 2. Now it's time to introduce the neural network to the real world. They use a data set based on randomly generated surfaces, like a bunch of different complex objects that it might encounter in a real-world scenario. This makes the network more robust and accurate.
So it graduates from the pool to the open ocean.
You got it. This two-stage training is key to making sure it can handle real electromagnetic scattering problems.
Okay, that makes sense. Now, we've talked about the neural network itself, how it learns, but remember, one of the big selling points of this method is its potential for parallelization. Can you explain what that means and why it's such a big deal?
Sure. Think about it like this. You have a huge, complex problem to solve, like simulating a really intricate object. Instead of one processor chugging away at it forever, you can split the problem up and have multiple processors work on different parts at the same time.
So it's like having a team of chefs working on different parts of a complicated dish, instead of just one chef trying to do it all.
Perfect analogy. This parallel processing can speed things up dramatically, letting you tackle problems that would have been impossible with traditional methods.
I'm starting to see how powerful this could be. Did they actually test how well their parallelization works?
They did. They simulated a large PEC sphere that was divided into multiple boxes, kind of like how MLFMA breaks down a problem. They looked at how long it took to calculate interactions with their method and compared it to a perfect parallelization scenario.
And did it live up to the hype?
It did. The computation time dropped significantly as they added more processors. There were some minor hiccups, but overall it scaled really well.
So they can actually achieve those huge speed boosts with parallel processing.
That's amazing. Okay, we've covered the basics of their approach, the neural network, the training, the parallelization. I'm dying to hear about the results they got. Did they only test this on a simple sphere?
Nope, they went way beyond that. They tested a variety of objects to show just how versatile and robust this method is.
Excellent. Let's dive into those results then. All right, they started with that PEC sphere we mentioned. They made it 2 wavelengths in diameter at a frequency of 1 gigahertz to make it a real challenge. That's a pretty big object to simulate.
No kidding. So they're not shying away from real-world scales here. How did their method stack up against those traditional approaches?
It was spot on. It perfectly matched both a 5-level MLFMA simulation and the analytical Me-series solution, which is the exact solution for a sphere. So it definitely passes the accuracy test.
Wow, that's impressive. How about the speed?
Well, in terms of iterations, their method actually needed slightly fewer iterations than the 5-level MLFMA to get to the solution. But the bigger difference was the time per iteration. Their method was a bit faster, and that was with 4 processors.
So they're already getting a speed advantage, but real-world objects aren't usually nice, neat spheres, right?
Exactly. So they also tested on the PEC-FLAM and NASA Almond models, which are much more complicated geometrically speaking. They're known to cause problems for traditional methods.
So no more spherical cows. Time to get real.
Exactly. Both the FLAM and Almond models were scaled to 2 wavelengths at 1 gigahertz, so still a pretty high frequency.
Okay, so we're talking complex shapes, high frequency. What were the results like for those?
Once again, really good. Their method produced results that were very consistent with those from a 4-level MLFMA simulation. They compared both the scattered electric field in the far zone and the current density on the surface of the object, which tells you how the waves are interacting with the surface details.
So their method is tough enough to handle those complex shapes. That's pretty cool.
It is. And get this, for both the FLAM and Almond, their method was significantly faster than the 4-level MLFMA, even on just one processor.
Wow, that's a big speed up. Why was it so much faster in those cases?
It goes back to that high aspect ratio we talked about. The FLAM and Almond models are both long and thin, and traditional MLFMA with its hierarchical structure just doesn't handle that well. But this new method, remember, it leverages symmetry. That helps it stay efficient even with those tricky shapes.
Makes sense. Okay, one last question. What about that low-frequency breakdown issue? Did they test how their method performed in those extreme cases?
Oh yeah, they definitely did. They went back to that PEC sphere, but this time they cranked the frequency way down, making the sphere just a tiny fraction of a wavelength. Traditional MLFMA just can't handle that at all.
So they were really putting their method through the ringer. How did it do?
It aced it. As expected, the traditional MLFMA completely bombed in that scenario. But their method, with its clever machine learning approach, matched the analytical solution perfectly. No low-frequency breakdown here.
That is incredible. It really shows how powerful this new method is.
Absolutely, it's a game changer for sure.
It's important to remember, though, that they're still working on a multi-level version of their method, kind of like the structure of MLFMA. So making direct comparisons with higher-level MLFMA, especially for really large objects, might not be totally fair just yet.
You're right, this is still early-stage research, and there's a lot more to come. But even so, their method is already faster than a 3-level MLFMA simulation on a single processor. And when you add in the benefits of parallelization, it becomes even more competitive.
It sounds like they're onto something truly groundbreaking here.
I think so too. This has the potential to revolutionize the world of electromagnetic simulations.
Welcome back, listeners. So we've been talking about this amazing new method using machine learning to tackle electromagnetic simulations. And man, it's really shaken things up.
It is. It's a super fascinating development.
We've seen how it beats those traditional methods
Yeah.
in terms of both speed and accuracy, especially for those really complex shapes and those tricky low frequencies. But I want to kind of zoom out for a second. Look at the bigger picture. What is this research, what does it tell us about the future of scientific computing in general?
That's a really great question. I think this paper, it's a perfect example of how machine learning is really changing the game in all sorts of scientific fields. I mean, traditionally, we've relied on these, these complex mathematical models, algorithms, to simulate physical phenomena.
Right, those huge equations that only supercomputers can even handle.
Exactly. And those methods, they're powerful, but they can be really computationally expensive. They take a lot of time, especially as the problems get bigger and more complex.
It's like trying to solve a giant jigsaw puzzle, but you only have a few pieces. You might get a tiny glimpse of the picture, but it's going to take you forever to see the whole thing.
That's a great analogy. Machine learning, it offers a totally different approach. Instead of, explicitly programming a computer to solve a problem step by step, we're basically teaching it to learn from data.
So it's like instead of giving the computer a set of instructions, we're giving it a textbook and saying, figure it out.
Yeah, exactly. In this case, the neural network, it's learning the physics of these electromagnetic interactions by analyzing a massive amount of data. Remember that Green's function we talked about? They use that to generate the data.
So it's like giving the computer a crash course in electromagnetism. Let it learn the rules of the game by observing tons and tons of examples.
Exactly. And once that network has learned the rules, it can make predictions, solve problems super fast, way more efficiently. It can bypass all those laborious calculations that traditional methods have to go through.
Okay, that sounds almost too good to be true. But it makes you wonder, could this mean like a shift away from those traditional methods in science and engineering?
It's definitely a possibility. We're already seeing machine learning being used in so many fields like fluid dynamics, material science, even drug discovery.
So it's not just limited to electromagnetism. This has far-reaching implications.
Absolutely. I mean, machine learning has the potential to revolutionize how we approach scientific discovery and problem solving across the board.
It's kind of mind-boggling when you think about it. But of course, with any new technology, there can be challenges, right? What are some of the hurdles that, that researchers might face in adopting this machine learning approach, more broadly?
Yeah, that's a great point. One of the biggest challenges is making sure the training data is really representative of the real-world problems we're trying to solve. If the neural network is trained on data that's biased or incomplete, it could lead to inaccurate, unreliable results.
So it's like training a self-driving car, but only in perfect weather conditions. It might be great on a sunny day, but as soon as it rains or snows, it's going to have problems.
Exactly. Another challenge is interpretability. Neural networks can be kind of like black boxes. It can be difficult to understand why they make certain predictions, which can raise concerns about their reliability, especially for critical applications.
So it's not enough for the neural network to just give us an answer. We need to understand its thought process, its reasoning. All right.
Right, especially in fields like medicine or engineering, where safety and reliability are super important.
That makes sense. Transparency and trust are key when you're using some powerful tools. Are there any other challenges or limitations that researchers might bump into as they explore this approach further?
Well, training these neural networks, it can still be pretty computationally demanding, especially for those really big, complex problems. The simulations are way faster once the network's trained, but that initial training phase can take a lot of computing power.
So it's like kind of an upfront investment. You need to put in the time and effort to train the network, but once it's ready, you get to benefit from its speed and efficiency.
Precisely. And, another potential limitation is that this method, at least in its current form, mainly focuses on what we call far-field interactions, the interactions between objects that are relatively far apart. Now, this is important for a lot of electromagnetic simulations, but there are cases where near-field interactions, those between objects that are close together, are really important too.
So it's like having a fantastic telescope to see distant galaxies, but you're missing a powerful microscope to look at the tiny stuff up close.
Yeah, that's a really insightful comparison, and addressing those near-field interactions is definitely going to be an important area of research moving forward.
It seems like there's still so much to explore and develop, but the potential here is just massive. As machine learning keeps advancing, I'm sure we're going to see even more innovative solutions popping up.
Oh, absolutely. And these advancements, they won't be limited to just electromagnetics. They're going to have a ripple effect across different scientific fields, leading to breakthroughs in areas like material science, drug discovery, climate modeling, you name it.
It's a pretty exciting time to be witnessing this fusion of machine learning and scientific computing. Feels like we're on the edge of a new era of scientific discovery, all powered by these new technologies.
I totally agree. And, this paper, it's not just a testament to human ingenuity. It's also a reminder that the journey of scientific exploration is far from over. There are still so many mysteries out there, challenges to overcome.
Speaking of challenges, let's go back to the paper for a minute. They tested their method on all sorts of objects and scenarios. Were there any results that really jumped out at you, like particularly impressive or surprising?
I was really fascinated by how well their method performed in those situations where traditional MLFMA just falls apart, like with the PEC sphere at that extremely low frequency.
Right, the one where MLFMA basically just gave up.
Exactly. That's where the real strength of this new method comes in. By directly evaluating the green's function during the training process, it just sidesteps the low-frequency breakdown problem completely. That's a huge breakthrough.
It's like they've found a way to climb a mountain that everyone thought was impossible to scale.
Exactly. And now we can accurately simulate what happens with electromagnetic waves in those low-frequency ranges, something that was really, really difficult, even impossible before.
It's not just making simulations faster. It's about opening up a whole new world of things we can simulate. That's a huge deal.
It is. And as these researchers keep refining their method and, develop that multi-level version we talked about, I think we can expect even more exciting applications to pop up.
I'm curious, what are your thoughts on how this research might impact the future of antenna design?
Oh, that's a great question. Antenna design is really complex, involves a lot of simulations to optimize performance. This new method could speed up that whole process, letting engineers try out more designs, find better solutions faster.
So it's like giving them a super-powered design tool.
Yeah.
They'll be able to create antennas that are smaller, more efficient, more powerful, all while saving time and resources.
Exactly. And that could lead to a whole new generation of antennas for all sorts of applications, from telecommunications and satellites to medical devices.
It's amazing to think about the ripple effect of this one research paper. And it's a great example of how, when different fields collaborate, you can get these amazing breakthroughs. You have the machine learning experts, the computational electromagnetics experts, all coming together to create something truly innovative.
Absolutely. It shows what's possible when you bring together diverse perspectives and skill sets to tackle those really tough problems.
It makes you wonder what other scientific mysteries are out there, just waiting for us to unlock them by, breaking down those barriers between different fields and encouraging more collaboration.
Oh, the possibilities are endless. I really believe we're at the beginning of an era of accelerated scientific discovery, driven by the convergence of different disciplines and these powerful new technologies like machine learning.
It's definitely an exciting time to be a scientist, an engineer, or just someone who's curious about the world around us. And speaking of curious minds, I'm sure our listeners are eager to learn more. We'll be sure to include links to the original paper and other resources in the show notes.
And in our next episode, we'll be taking an even deeper dive into some of the technical details and talking about where this research might go in the future. So stay tuned for more on the fascinating world of machine learning and scientific computing.
This has been such a great conversation so far. But before we jump to the last part of our deep dive, I want to leave our listeners with something to think about.
Oh, I like that. A final thought-provoking question to keep them engaged.
Exactly. So here it is. Could this method, with all its advantages, the accuracy, efficiency, and versatility, could it actually become the new standard for electromagnetic simulations? Could it replace, or at least significantly change, those traditional methods that we've relied on for so long. What do you think, listeners? We'd love to hear your thoughts.
That's a fantastic question, and we're going to explore it even further in the next segment. See you soon.
Welcome back to the deep dive. It's been quite a journey, exploring this revolutionary method that's kind of bringing machine learning into the world of electromagnetic simulations.
It really is exciting, and the implications are huge.
We've seen how it can outperform those traditional methods, how it's pushing the boundaries of what's possible in scientific computing. And now, in this final part of our deep dive, I want to shift gears a little bit. I want to talk about what it all means for you, the listener.
I like that, bringing it all home.
Exactly. We've gone through the technical details, talked about how this could benefit researchers and engineers. But let's just take a minute. Imagine how this technology could actually impact our everyday lives.
I'm ready. Let's get into it.
Imagine a world where electromagnetic simulations, they're not a bottleneck anymore, where we can design and optimize those complex systems super fast with incredible precision. What would that world look like? What new possibilities would be open to us?
That's the big question, isn't it? The possibilities are pretty mind-boggling.
Let's start with something we all use every day, our smartphones. Imagine antennas that are so efficient, so compact, that they just blend right into the device. And you get lightning-fast data speeds, battery life that lasts for days, no more searching for a signal, no more worrying about your phone dying in the middle of the day.
That would be a game changer for sure. And it's not just about convenience, it's about staying connected, right? I mean, reliable, high-speed internet access is becoming essential in our world.
Absolutely. It's about staying connected to the people and information that matter most. But let's think beyond our phones for a second. What about healthcare? What if we had MRI machines that were faster, more accurate, and less intrusive? Or imagine targeted therapies that use these precisely focused electromagnetic waves to, eliminate cancer cells without harming the healthy tissue around them.
Those are some incredible advancements to think about. I mean, early diagnosis, accurate diagnosis, that can make a huge difference for so many people. And those targeted therapies offer hope for better, less invasive treatments for so many diseases.
It's amazing to think how this technology could really impact human health and well-being. But of course, the possibilities don't end there. What about renewable energy? Imagine solar panels that are even more efficient at capturing sunlight, or wind turbines that are designed to squeeze out the maximum amount of energy from even a gentle breeze.
Those are the kind of innovations that can really help us build a more sustainable future. We're facing some serious environmental challenges, and this technology could be a big part of the solution.
It's not just about saving the planet, though. It's about creating a better future for all of us. A future where we can meet our energy needs in a way that's good for the environment and makes economic sense.
It's a future worth fighting for.
It is. And those are just a few examples. The potential applications for this technology are huge, and we're just scratching the surface. It really could touch every aspect of our lives.
I totally agree. It really speaks to human ingenuity and the incredible things that can happen when we bring different fields of knowledge together.
Well, we've covered a lot of ground in this deep dive. We've talked about this new method, its potential to revolutionize electromagnetic simulations, and how it could impact our world in so many different ways.
It's been a fascinating discussion.
It has. And on that note, I want to thank you, the listener, for joining us on this incredible journey. We hope you found it informative, inspiring, and maybe even a little mind-blowing. It's been a real pleasure sharing these ideas with you.
It has, and we look forward to exploring more cutting-edge topics with you in the future. Until then, keep asking questions, stay curious, and keep diving deep.
Welcome back, everybody. We're diving deep today into a paper that really caught my eye. It's tackling a problem that's been kind of a thorn in the side of computational electromagnetics for quite a while. How to solve those integral equations that pop up when you're dealing with electromagnetic scattering problems, especially for those really big, complex structures.
Yeah, definitely a challenge.
For sure. And the title of this paper is a bit of a mouthful, gotta admit. It's called A Novel, Highly Parallelizable Machine Learning-Based Method for the Fast Solution of Integral Equations for Electromagnetic Scattering Problems.
Quite a title.
Definitely ambitious.
Yeah, it was just published this month, January 9th, 2025, to be exact, by Ines Kos, Mert Kalfa, Cecil E. Dogan, and Vakur B. Ertürk. So it's fresh off the press.
Oh, wow. Very recent.
Yeah. So before we jump into the details, I think it would be helpful to set the stage a bit, remind ourselves why solving these integral equations is so important in the first place. Right. Well, think about it. Simulating things like antennas, radar systems, even those medical imaging devices, all of that hinges on understanding how electromagnetic waves scatter off of objects. And the math behind all of that, the way we describe those interactions, that's where integral equations come into play. They are essential tools, but they can get really messy, especially when you're dealing with large or intricate shapes.
Absolutely.
Yeah.
I mean, we've got methods like the multi-level fast multipole algorithm, MLFMA for short, but even those can become computationally expensive when you're dealing with really complex problems.
Yeah, for sure. And then there's that issue of low frequency breakdown. MLFMA doesn't always perform well when you get down to those lower frequencies.
Right, right. Accuracy takes a hit. So with all that in mind, what are these researchers proposing? What's their new angle?
Well, they're introducing a really interesting approach that uses machine learning to speed up these calculations within what we call the method of moments framework.
Machine learning. That's really fascinating. I'm really intrigued to see how they're applying that to this particular problem. How does that even work? Could you give us a high-level overview?
Yeah, so their method basically starts by representing the geometry of the scatterer, the object that the waves are hitting, using a collection of, get this, uniformly distributed Hertzian dipoles.
Okay, so they're simplifying the problem by breaking it down into these, I guess you could call them mini antennas.
Yeah, you can think of them as these tiny antennas. Each one radiates a very simple electromagnetic field.
Okay, I'm starting to get the picture. But why Hertzian dipoles? What's special about them in this context?
Well, they're chosen because they're like the most basic type of antenna, theoretically speaking. We understand their behavior really well. The equations that describe them are pretty straightforward too, so they make a great starting point for representing more complex fields.
Ah, I see. It's like using simple Lego bricks to build something really intricate.
Exactly. It's a really clever way to take this complex problem and translate it into something that machine learning algorithms can work with.
So they've got these dipoles, they've simplified the geometry, but how do they actually use machine learning to do the heavy lifting, the actual calculations?
It's a three-stage process. The first stage is all about mapping the original complex geometry of the scatterer onto this uniform grid of Hertzian dipoles. You can kind of think of it like converting a really high-resolution image into a grid of pixels. Each pixel represents one of those dipoles with a certain strength and orientation.
So they're making a simplified representation of the scatterer that still captures the essential information about its electromagnetic property.
Yeah, exactly. They're capturing the essence of the scatterer.
Okay, what's the next step?
The second stage is where things get really interesting. This is where the machine learning really kicks in. Traditionally, to figure out how all those dipoles in the far zone interact, the area far away from the scatterer, well, that would require tons of calculations. It can get very computationally heavy. But these researchers found a way to shortcut that. They figured out how to use pre-calculated matrices to capture those interactions. It's like having a lookup table where you can quickly find how two dipoles will affect each other based on their distance and orientation.
Okay, that's clever. So instead of doing complex calculations every time, they can just refer to this table and boom, they've got their answer much faster.
Exactly. But there's a catch. Even with these matrices, there can still be a ton of them, especially if you're dealing with a big problem. That's where the machine learning comes in. They train what's called a complex-valued, fully connected neural network, or CVFCNN for short, to predict those matrices.
Oh, wow. So they're training a network to mimic those complex electromagnetic calculations. That's pretty wild.
Yeah, it's pretty amazing. The network learns all of those intricate relationships between the dipoles.
I'm starting to see how the pieces fit together here. But how do they make sure this neural network is accurate, that it can be trusted to handle these complex calculations?
That's where their two-stage training strategy comes in. First, they train the network on a data set of uniformly generated data, just to give it a good, broad understanding of how dipoles interact in general, regardless of the specific geometry of the problem.
So it's like teaching it the fundamental rules of electromagnetism.
Right. And then they take it a step further. They fine-tune the network using a more specialized data set based on what they call pseudo-randomly generated surfaces. This exposes the network to more realistic types of current distributions, the kind of situations it's likely to encounter when dealing with real-world problems.
So it's like boot camp for the neural network. They make sure it can handle the real deal.
Yeah.
Okay, so they've got their dipoles, they've trained their neural network. What's the final step? How do they get back to the actual solution of the original problem.
That's the third stage. It's called inverse mapping. They basically translate the fields that the neural network has predicted back into the language of the original subdomain functions. It's like reversing that simplification process from the first stage.
So they go from complex to simple, then back to complex again.
Right. And it's all thanks to that clever use of machine learning that they're able to do this efficiently.
This is all incredibly fascinating. I'm really starting to see how this method could revolutionize things. But before we get carried away with the possibilities, let's dig a little deeper into the nitty-gritty details. Let's talk about the math. They mentioned in the paper that they represent the current distribution within a box, one of those little sections of the scatterer, using a set of Hertzian dipoles. Can you unpack that a little for us? What does that mean, mathematically speaking?
Sure. They start with the idea that the current distribution within a box, and they denote that with overline, can be represented as a sum of subdomain basis functions. They show this in equation 3 of their paper. Overline represents the nth subdomain basis function, and $1 is the corresponding coefficient. What they're trying to do is replace those subdomain basis functions with a fixed number of Hertzian dipoles.
Okay, so they're approximating that complex current distribution using a set of simpler known functions. What's the advantage of doing that?
Well, the main advantage is that Hertzian dipoles are, they're relatively easy to work with mathematically. We know how they behave. Their fields are described by some pretty simple equations, so they make a great choice for representing more complex electromagnetic fields. And then the challenge becomes figuring out what are the optimal strengths and orientations of these dipoles to best capture that original current distribution.
Right, that makes sense. And that's what they're doing in that mapping to uniform basis functions stage, right? They even talk about using the dyadic Green's function in that step. Can you tell us more about that? What role does that function play?
Sure. So the dyadic Green's function, which they represent with overline in their equation 4, is super important for calculating the electric field generated by both the original current distribution and that array of Hertzian dipoles. It basically describes how a point source of current at some location overline $ influences the electric field at another point overline.
Okay, so they're using this function to compare the electric fields produced by both representations, the original one, and the dipole approximation, and then they're trying to minimize the difference between the two.
Exactly. They lay out how they calculate those electric fields in equations 4 and 8. Then, to find the best coefficients, those $1 values for the Hertzian dipoles, they use a least squares method, which they detail in equations 9 and 10. This ensures that the dipole representation they come up with accurately captures the electromagnetic behavior of the original current distribution.
It's a really neat trick to bridge that gap between the complex and the simple. Okay, so they've translated the problem into the language of Hertzian dipoles. Now let's talk about that translation stage where the machine learning really comes into play.
Right. Now we get to those translation matrices we talked about earlier. These matrices, which they denote with overline in equation 13, are basically a shorthand way to describe the interactions between dipoles that are located in different boxes. Each element of the matrix tells you how much influence a dipole in one box has on a dipole in another box.
Okay, so each matrix is basically encoding a bunch of calculations about those dipoles, how they affect each other based on their positions and orientations, and this is what they're trying to predict with machine learning.
Yes, that's exactly it. The matrix multiplication in equation 13 is what they're aiming to speed up with their machine learning model.
Got it. So are they pre-computing all of these matrices beforehand, or is that what the neural network is doing?
It's a combination of both. They do some pre-computation, but they also use symmetry to cut down on the number of unique matrices they need to worry about. Because those boxes are arranged in a uniform grid, a lot of those dipole interactions are equivalent, so they don't have to compute every single one.
Smart. Less work for the computer. But I'm guessing even with the symmetry, calculating all those matrices using that dyadic Green's function would still take a lot of time. That's where the neural network comes in, right?
Right. Instead of grinding through all of those calculations, they train the CVF-CNN to predict those matrix values. It's shown in Figure 5 of the paper. Essentially, this neural network learns the complex relationship between the positions of the dipoles and their interactions, so it acts as a fast approximation for those more tedious calculations.
Wow. They're teaching a network to understand electromagnetics, or at least that aspect of it. That's impressive.
It is pretty amazing.
And I'm guessing that's where their two-stage training process comes in again, right? Making sure the network is up to the task.
Exactly. That two-stage process is really important to make sure the network can handle those real-world scenarios accurately.
Okay, so they've mapped everything onto dipoles. The neural network is doing its prediction magic. What's the final step? How do they get back to an actual solution for the problem they're trying to solve?
So the last stage is called inverse mapping. And in this stage, they take the fields that were calculated using those neural network predictions and translate them back into the original subdomain functions. Think of it like taking those pixels we talked about earlier and merging them back together to reconstruct the whole image.
Ah, so they go from complex to simple and back to complex again.
Right. But this time, they've got all those electromagnetic interactions accounted for thanks to the machine learning.
This is really ingenious stuff. They've managed to take this computationally intensive problem and streamline it in a really elegant way.
Yeah, it's a really impressive approach.
I'm excited to dig into the details of how this method actually performs, how it stacks up against those traditional methods like MLFMA. But I think we've covered a lot of ground already in this first part of our deep dive.
Definitely. It's a great start. So yeah, picking up where we left off, we were just starting to talk about how they move from this dipole representation to the real heart of their method, that translation stage.
Right. And a key part of that stage is those translation matrices you mentioned. They basically hold the instructions for how to calculate the interactions between all those dipoles. Can you remind us what those matrices represent and how they fit into the big picture?
Okay, so those translation matrices, denoted as overline their equation 13, basically contain all the information about how the electric fields radiated by those Hertzian dipoles, which are located in different boxes, interact with each other. Each element in one of these matrices tells you how much influence a dipole in, say, box I has on a dipole in box J.
So it's like they've created a pre-computed guide for how those dipole fields interact across different locations within the scatterer. Why is that so important?
It's important because if you were to directly calculate those interactions every single time using that dyadic Green's function, especially if you have a lot of dipoles, it would just be way too computationally expensive. Those calculations would take forever. But with these pre-computed matrices, they've created this shortcut that makes the calculations much, much faster.
Okay, so I see the efficiency aspect. But practically speaking, how do they actually use these matrices in their calculations?
Well, they use those matrices to calculate the interaction between the electric fields of those boxes in the far zone. If we look at equation 13 from their paper, overline ruckus, sum AY, overline IY, I neck, overline IY, we can see they're basically doing a weighted sum. Here, overline RY is the electric field at a point overline that's due to those Hertzian dipoles in box J. Non-box is the total number of boxes, and overline Y represents a vector containing the coefficients for those Hertzian dipoles in box J.
So they're adding up contributions from all the other boxes, each one weighted by this translation matrix. Makes sense.
Exactly. And this is where the machine learning aspect comes in. Instead of calculating every single element of those overline orator matrices, which can be a real pain, they use a complex-valued, fully connected neural network, CVFCNN, to predict them.
Ah, right. So they're essentially training this neural network to understand how those dipole interactions work. But wouldn't they need a massive amount of data to train a network that can actually predict these complex interactions?
That's a good point, and that's exactly why they came up with this two-stage training strategy. First, they train that CVFCNN using a dataset of uniformly distributed Hertzian dipoles. This allows the network to kind of get a grasp of the basic principles behind those dipole interactions.
So they're like giving it a foundational understanding of electromagnetic theory before getting into the specifics of the problem.
Yeah, exactly. It's like building a base of knowledge. Then, for the second stage, they take it up a notch. They fine-tune the network using a data set based on something called pseudo-randomly generated Peck surfaces.
Ah, so they're introducing the network to more realistic situations, scenarios that it might actually encounter when dealing with real-world problems.
Right, preparing it for the real world.
What kind of architecture are they using for this neural network? Is it anything special?
They're using a pretty straightforward architecture for their CVFCNN. If you look at figure 5 in the paper, you can see it only has a single hidden layer with a specific activation function called the Cartesian rho LU.
Okay, is there a reason why they went with that particular architecture and activation function?
Well, when it comes to neural networks, choosing the right architecture is a bit of an art and a science. In this case, I think they probably opted for a simpler architecture, like the single hidden layer, because it strikes a good balance between being complex enough to learn those interactions, but also being computationally efficient.
And what about that Cartesian RailU activation function? What's the deal with that?
The Cartesian RailU is really handy for dealing with complex valued inputs and outputs, which you always encounter with electromagnetic fields. It essentially applies that RailU function, you might have seen it in other neural network stuff, separately to the real and imaginary components of the complex number.
Ah, I see. Makes sense. They need something that can handle those complex numbers that are essential for these kinds of calculations. So they train this network offline, and then during the actual simulation, they can quickly predict those translation matrices on the fly.
Exactly, and this approach has some pretty big advantages. For one, it saves a ton of time and computational power because you don't have to calculate those matrices directly. And it allows them to solve those problems where traditional MLFMA kind of falls apart, especially at those lower frequencies.
Now, you mentioned low-frequency breakdown a couple of times. Can you explain a bit more about why traditional MLFMA has trouble with those lower frequencies and how this new method gets around that problem?
Sure. So traditional MLFMA relies on something called multipole expansions, which are basically mathematical series that approximate the fields far away from the source. But at low frequencies, those expansions become less and less accurate. That's because the wavelengths get really big, much bigger than the size of the object itself.
Ah, so it's like trying to use a really blunt tool to do something that requires a lot of precision.
Exactly. But the method they present in this paper, it's based on directly representing those fields using those Hertzian dipoles, and that approach doesn't suffer from that same low-frequency breakdown that you get with the multipole expansions.
So they've managed to overcome a pretty significant hurdle in computational electromagnetics with this dipole machine learning combo.
Yeah, it's a pretty big deal, and they actually show in their paper that their method can accurately simulate scatterers at those low frequencies where MLFMA just can't keep up.
Very cool. Now, before we move on to the last stage of their method, I want to circle back to parallelization. They make a point of saying their method is highly parallelizable. What does that mean exactly, and how do they achieve it?
Okay, so the key to their parallelization scheme is that the structure of all those boxes, after they've been mapped to those Hertzian dipoles, it's identical. Every box looks the same. This means you can perform the computations for each box independently and simultaneously, like on different processors.
So it's like having a whole team of workers, each tackling a small part of the problem at the same time.
Exactly. It's a divide and conquer strategy. And this leads to some pretty impressive speedups, especially for those really big problems where you can spread the workload across a lot of processors. They actually show in Figure 8 that they achieve almost linear speedup as you increase the number of cores.
That's really efficient.
Yeah.
It means their method can handle those increasingly complex problems without getting bogged down. Okay, I think we've got a good handle on that translation stage now. So let's move on to that last stage, the inverse mapping. If I remember correctly, it's kind of like the first stage, but in reverse. Can you walk us through it?
You got it. That inverse mapping stage is where they essentially decode the electric field that they calculated using those neural network predictions back into those original subdomain functions. You have to do that because you want the solution in terms of the original problem's variable.
Right. It's like bringing it back to the language of the original problem after simplifying it with those dipoles. Yeah. How do they do this, mathematically speaking?
They use a least squares approach again, similar to what they did in the first stage. If you look at equations 1517 in their paper, you can see the details. They basically express the electric field at those desired integration points on the original subdomain function, which they represent with overline equation 15 in terms of the electric fields produced by those Hertzian dipoles. Then they use a least squares solution, as shown in equations 16 and 17, to find the best fit between those two representations.
It's like solving a puzzle, right? They have the electric field at certain points, and they need to figure out how to best represent that field using those original subdomain functions.
Exactly. It's all about making sure the solution is consistent and accurate, and that it translates seamlessly back from that simplified dipole world to the original problem.
This whole three-stage process is so clever. They've really found a way to integrate machine learning into what's typically a very computationally heavy problem. And they've done it in a way that's both elegant and efficient. But I'm curious, how do they actually demonstrate that this method works? What metrics are they using to show that it's effective?
Okay, so they use a couple of metrics to evaluate how well their method performs. First off, there's accuracy. They compare their results to established analytical solutions, like those Me-series for spherical scatterers, and to numerical methods like MLFMA. And they show that their methods' results agree really well with those existing solutions across a variety of frequencies and scatterer shapes.
That's reassuring. It means they're getting results that are consistent with what we already know to be true. But accuracy is just one piece of the puzzle. How do they assess the efficiency of their method?
Well, efficiency is mainly measured in terms of computational time. They compare how long it takes their method to solve a given problem to how long it takes traditional MLFMA to do the same thing. And as we've talked about, they found some pretty significant speedups, especially for objects with those high aspect ratios and at those low frequencies where MLFMA really struggles.
That's a big win. Being able to solve those problems faster opens up a whole world of possibilities for doing even bigger and more complex simulations.
Exactly. And don't forget, their method can be parallelized, so they can distribute those calculations across multiple cores, which makes it even faster.
Right. Okay, I think we've covered a lot of the theoretical and implementation details, but before we wrap up this part of the deep dive, I want to take a closer look at some of the actual results they present in their paper. There are quite a few graphs and figures in there. Could you walk us through some of the key ones and explain what they're showing us about the effectiveness of this method?
Of course. Let's start with Figure 7, which shows how well that CVF-CNN is learning during training. It shows the convergence for both the uniformly distributed dataset and the pseudo-randomly generated PEC surface dataset.
Okay, break that down for us a little. What are we seeing in this figure and why is it important?
So the figure shows how the mean squared error, or MSE, changes as the network is trained. MSE is just a way to measure how close the network's predictions are to the actual values. We can see that the MSE for both datasets drops pretty quickly at the beginning, which means the network is learning the patterns in the data. And the MSE for that uniformly distributed dataset converges faster, which makes sense because it's a simpler dataset. But the MSE for the PEC surface dataset, even though it's a little slower, it gets really low eventually. This means the network is doing a good job of learning even those more complex, realistic scenarios.
Okay, so this figure is basically confirming that their two-stage training strategy is working. The network can learn those fundamentals from a simple dataset and then fine-tune itself using that more complex dataset for real-world accuracy.
Yep, exactly. It's a really efficient way to get high accuracy without spending forever on training.
Now, how about figure 8? You mentioned that one earlier when we were talking about parallelization. What's that figure showing us?
Right, Figure 8 shows how well the parallelization scheme works. It basically plots the speedup they achieve as they increase the number of cores used in the simulation. The best case scenario is what we call linear speedup, which means that if you double the number of cores, the computation time gets cut in half.
And are they getting close to that ideal linear speedup?
They're getting pretty darn close. They're seeing near linear speedup, which is fantastic. It means they've come up with a really effective way to divide up those calculations and utilize the power of multiple processors.
That's great news for people working with these really big problems. Cutting down that simulation time can make a huge difference. Okay, let's look at some of the figures that compare their method's accuracy to those established solutions. They talk about comparing their results to the Me series and traditional MLFMA. Can you show us some of those comparisons?
Yeah, definitely. Figures 9 and 10 are good examples. Figure 9 shows what's called the bistatic radar cross-section, or RCS, for a PEC sphere calculated using their method, the Me series, and MLFMA. RCS is basically a measure of how detectable an object is by radar. And Figure 10 shows a similar comparison, but for a dielectric sphere.
And what are those figures telling us about their method's accuracy?
Well, if you look closely at those figures, you can see that the results from their method are almost perfectly aligned with the Me series and MLFMA results. The curves are practically on top of each other. This tells us that their method is producing really accurate results.
That's very compelling. It shows that their method can compete with those well-established, commonly used techniques. Are there any other figures that you think really showcase the strengths of their method?
Yes, Figure 16 is particularly interesting. It shows the bistatic RCS for a PEC sphere that has a diameter of only 64, calculated using their method and MLFMA.
Okay, what's so special about this particular case?
This case is really important because it demonstrates how their method can handle that low-frequency breakdown problem that we talked about earlier. Remember, traditional MLFMA has a really hard time with those low frequencies.
Right. And you can really see that in Figure 16. The MLFMA results are way off, but their method is still producing accurate results.
Exactly. This figure really highlights how robust and versatile their method is, especially when you're dealing with those situations where the traditional techniques just don't work.
I'm really impressed with how thoroughly they've evaluated their method. They've compared it to analytical solutions, existing numerical methods, and they've even shown that it can handle those tricky low-frequency cases.
I agree. They've done a great job demonstrating that their method is accurate, efficient, and has a wide range of application.
Okay, so we've covered a lot of ground here. We've gone over the theory, the implementation, the results. It's clear that they've come up with a really clever way to bring machine learning into this traditionally computationally demanding problem, and they've gotten some really great results.
Yeah, it's some really impressive work. It has the potential to really change things up in computational electromagnetics.
I'm curious to hear what you think about the broader implications of this research.
Right.
What could this lead to? What are some of the potential future directions for this work?
That's a great question. There are definitely a lot of exciting avenues to explore now. One that they mention is developing a multi-level hierarchical version of their method, similar to traditional MLFMA.
So taking the best of both worlds.
Exactly. That would be really cool to see. If they can pull that off, it could lead to even greater efficiency, especially for those massive, massive problems where MLFMA still has an edge.
It would also be interesting to see if they can apply this method to other types of integral equations, not just the ones they focused on in this paper.
Definitely. There are so many different types of integral equations that are used in electromagnetics. Seeing how well their method generalizes to those would be really valuable.
And of course, there's always room for tweaking and optimizing that neural network architecture. Maybe a different architecture could give them even better accuracy or efficiency.
Oh, absolutely. There's so much to explore there. I think we're going to see a lot of interesting developments in that area.
It's like they've opened up a door to a whole new world of possibilities.
And I, for one, am really excited to see what those possibilities are.
Me too. It's been a really fascinating deep dive so far, and I think it's safe to say that the future of computational electromagnetics is looking pretty bright.
I agree completely. It's a very exciting time to be working in this field.
Okay, so we've really gotten into the weeds with this research, but I think it's time to step back and look at the bigger picture.
Yeah, I agree. It's good to zoom out every now and then.
Exactly. So for our listeners out there, what's the main takeaway from all of this? Why should they care about Hertzian dipoles and neural networks and all of this stuff?
Well, I think if you're working in any field where you use electromagnetic simulations, things like antenna design, radar systems, medical imaging, anything like that, this research could have a big impact on your work.
Because it could mean those simulations could become faster and more accurate.
Exactly. Especially for those tough problems, like when you're dealing with really large structures or those low frequencies where those traditional methods just don't cut it. This new approach could be a real game changer.
It's almost like they've found a way to translate those super complex electromagnetic interactions into a language that machine learning can understand, right?
Yeah, that's a great way to put it. And by doing that, they've opened up all sorts of new possibilities for tackling these computationally demanding problems.
It really makes you wonder what other scientific challenges could benefit from a similar approach.
Oh, absolutely. I think we're just scratching the surface of what's possible when we start combining machine learning with those more traditional scientific computing methods.
It's a really exciting time to be following these advancements, for sure. Speaking of advancements, the researchers do mention some future directions for this work. What are you most curious about?
Well, I'm really intrigued by that idea of creating a multi-level hierarchical version of their method, like they mentioned. Combining their approach with the structure of traditional ML-FMA.
Yeah, getting the best of both worlds.
Exactly. If they can make that work, it could lead to even more efficiency, especially for those huge, massive problems where ML-FMA still has an advantage.
I'm also really curious to see if they can apply this to other types of integral equations beyond the ones they looked at in this paper.
Oh, yeah, that's a great point. There's a whole world of integral equations out there in electromagnetics. It would be really interesting to see how their method performs with those.
And of course, there's always that question of the neural network architecture itself. Could they get even better results with a different architecture?
Definitely. There's so much room to explore there. I'm sure we'll see a lot of new developments in that area.
It's like they've opened a door to a whole new room full of possibilities.
And I can't wait to see what researchers find as they start exploring that room.
Me too. This has been a fantastic deep dive, and I think it's safe to say that the future of computational electromagnetics is looking brighter than ever.
I completely agree. It's a really exciting time to be working in this field. I have no doubt that we're going to see even more amazing discoveries as we combine machine learning with those traditional scientific computing methods.
So to our listeners, if you're as fascinated by this research as we are, we highly encourage you to check out the full paper. It's packed with details and insights that we just couldn't cover in our deep dive today.
And maybe this research will inspire you to ask new questions in your own field. What other computationally intensive problems could benefit from a similar approach? The possibilities are truly endless.
That's a great point. Always be curious, always be exploring. Who knows, maybe you'll be the one to make the next big breakthrough. Until next time, fellow knowledge seekers, keep diving deep.